Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the cold spaces between stars, where objects older than memory drift through the galaxy's patient dark. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The object that will come to be designated 3I/Atlas, the third confirmed interstellar visitor to pass through the solar system, announces itself first not with fanfare but with pixels. A sequence of images captured by the asteroid terrestrial impact last alert system in Hawaii shows a faint smudge moving against the fixed stars. The smudge does not follow the rules. Its trajectory, when traced backward through the mathematics of orbital mechanics, does not close into an ellipse around the Sun. Instead, the path opens into a hyperbola, a curve that arrives from infinity and returns to infinity, never bending into capture, never slowing into orbit. This is how the universe delivers its mail, quietly, without return address, across distances so vast that the light from nearby stars takes years to cross them. The object moves through the outer solar system at a velocity that speaks of origins elsewhere. Somewhere, perhaps dozens or hundreds of light years away. This fragment of ice and rock and organic carbon was born in the swirling disk around a star that humanity will never name. It formed in darkness, in cold, in a region of space where the temperatures hover only degrees above absolute zero, where molecules move with the lethargy of deep time. The astronomers who first noticed the anomaly are not looking for interstellar objects. They are looking for asteroids, for near-Earth threats, for the comparatively mundane hazards that orbit within the Sun's gravitational dominion. But the software that analyzes the images is patient, compares each frame to the last, subtracts the stars that do not move, and isolates the things that do. When the motion of 3I/Atlas is plotted, the numbers do not fit. The eccentricity of its orbit exceeds 1, the threshold that separates the bound from the unbound, the solar from the extrasolar. Only took 4 billion years of planetary science to build telescopes sensitive enough to notice. The universe seems to murmur. The discovery is reported in the usual channels. Observatories around the world turn their instruments toward the coordinates. Follow-up observations refine the trajectory, tighten the uncertainties, confirm what the initial data suggested. The object is moving too fast. Its velocity relative to the Sun is consistent with an origin in the local standard of rest, the average motion of stars in the Sun's neighbourhood of the galaxy. This is not debris kicked out from the Oort cloud by a passing star. This is not a comet perturbed into an unusual orbit by Jupiter's gravity. This is something that has been travelling through interstellar space for timescales that dwarf the existence of human civilization. The path, when extrapolated, comes from a point in the sky above the plane of the ecliptic. Most objects in the solar system orbit near the ecliptic, the flat disk inherited from the solar nebula's rotation. But 3I/Atlas arrives from a steep angle, as if it has no memory of the Sun's disk, no connection to the architecture of planets and asteroids and comets that grew from the same primordial cloud. It moves through the solar system like a visitor who does not know the neighbourhood, who arrived by a different road entirely. The Milky Way contains perhaps 400 billion stars. Around many of those stars, planets form, or fail to form, or form and then are destroyed, or form and eject material during violent collisions and gravitational reshufflings. Some of that material escapes. It escapes into the space between stars, where gravity loosens its hold and velocities carry fragments across parsecs. The galaxy, in this sense, is not a collection of isolated solar systems, but a medium through which matter circulates. Slowly, across spans of time that make geological epochs seem brief, only took a few million years to cross from there to here, wherever there was. When 3I/Attilus was forming, the Sun may have been elsewhere in its orbit around the galactic centre. Stars drift. The Sun completes one orbit around the Milky Way roughly every 230 million years, a period sometimes called a cosmic year. In the time since Earth's Permian period, the solar system has completed one full lap. In the time since 3I/Atlas was ejected from its birth system, the Sun and that distant star may have moved in different directions, their relative positions shuffled by the slow gravitational choreography of the galaxy's spiral arms. No one knows which star. The trajectory can be traced backward, but uncertainties compound. Small errors in measuring the object's velocity today become large errors when projecting its position millions of years ago. The galaxy does not keep records. Stars do not leave forwarding addresses. The object arrives, and its origin remains one of those quiet mysteries that astronomy catalogues but cannot resolve. Not yet. Perhaps not ever. The ironies accumulate like frost. An object from another solar system, carrying information about processes that occurred light years away, passes through our neighbourhood and is detected only because a survey designed to protect Earth from asteroid impacts happens to be watching the right patch of sky at the right time. If the survey had been pointed elsewhere, if the object had passed a few years earlier or later, it would have slipped through unnoticed, one more ghost among countless others that drift through the dark and leave no trace. Only took 8 minutes for light to travel from the object to Earth, and 4 billion years for the object to travel from there to here, more or less. The name itself, 3I/Atlas, is a catalogue entry, not a story. The 3I denotes the third interstellar object confirmed by the International Astronomical Union. The Atlas refers to the survey that found it. There is no mythology here, no ancient narrative, only the bureaucratic poetry of astronomical nomenclature. The first interstellar object, 1I/Oumuamua, was discovered in 2017, the second, 2I/Borisov, in 2019. The intervals between discoveries are shortening, not because interstellar objects are arriving more frequently, but because humanity's ability to detect them is improving. The sky survey technology grows more sensitive, the algorithms more sophisticated, the network of observatories more coordinated. How many others have passed through, undetected, in the centuries before anyone thought to look? The object tumbles. Its light curve, the pattern of brightness changes over time, shows periodic variation. This is the signature of rotation, of a body that is not spherical, that presents different cross-sections to the Sun as it spins. The rotation period is not yet well constrained. Early estimates suggest hours to days. The tumbling is not smooth. The object does not spin around a single axis like a top, but wobbles, its rotation complex, perhaps chaotic. This is what happens to small bodies that have experienced collisions, torques, outgassing events. The object's spin state carries a history written in angular momentum, in the distribution of mass, in forces applied over time. Somewhere in its past, something happened. Perhaps it collided with another object in its birth system. Perhaps it was grazed by a gravitational encounter that set it tumbling. Perhaps its own outgassing, if it is volatile rich, has torqued its spin over millions of years. The tumbling continues, patient and indifferent, as the object crosses the solar system and heads back into the spaces beyond. The brightness of 3I/Atlas changes, but not in the way that dead rock changes brightness. Dead rock reflects sunlight predictably, its brightness varying only with distance and rotation. But the light curve of this object shows something else. Sudden brightenings, asymmetries in the peaks and valleys of reflected light, deviations from the smooth sinusoid that a bare, rotating body would produce. These are the signatures of activity. The object is shedding material. It is outgassing. A coma, a cloud of dust and gas, surrounds the nucleus, scattering sunlight in ways that depend on particle size, composition, the geometry of the jets that release them. Observatories in Chile, Arizona, and the Canary Islands point their instruments toward the coordinates. Photometric monitoring begins. Long sequences of images taken through different filters, measuring brightness in ultraviolet, visible, and near-infrared wavelengths. The data accumulate in archives, each observation adding a point to the graph of how the object's appearance changes over time. The light curve is not periodic in a simple sense. There are fluctuations on short timescales, hours, and trends on longer timescales, days to weeks. The brightness increases as the object approaches the sun, then fades again as it recedes. But the fade is slower than expected, as if the coma persists longer than it should, as if the dust does not dissipate quickly. Only took a few decades of CCD technology and digital imaging to make these measurements possible, after millennia of naked-eye astronomy that could never have detected such subtleties. The tumbling affects what can be seen. As the object rotates, different parts of its surface point toward the sun, and different regions may be more or less active. Some comets have jets that erupt from specific locations, ancient impact sites, fractures in the crust, regions where volatile ices lie closer to the surface. If 3I/Atlas has such features, they rotate in and out of sunlight, their contributions to the coma waxing and waning with the spin. Observers try to disentangle the rotation signal from the outgassing signal, to separate geometry from activity, but the data are noisy. The object is faint, even at its brightest. It requires large telescopes and long exposures. Every measurement is a contest between signal and noise, between the faint photons arriving from the object and the background glow of the sky. Astronomers who study these light curves speak in careful language. They say, possibly, tentatively, consistent with. The uncertainties are large. The observations are difficult. The object is small, distant, and does not cooperate by holding still or simplifying its behaviour. But patterns emerge. The amplitude of the brightness variation suggests an elongated shape, perhaps 2:1 or 3:1 in its longest to shortest dimensions. Elongated objects are not uncommon among small bodies. Collisions break things into irregular chunks. Gravitational reshaping only occurs for objects large enough that their own gravity can overcome the strength of rock and ice. 3I/Atlas is too small for that. It retains whatever shape it was given by the forces that created it. Impact, tidal disruption, thermal fracture, the slow work of sublimation eroding weaker layers. Only took a few billion years of collisions to produce this particular lump. The activity itself raises questions. Comets outgas when sunlight warms their surfaces and volatile ices sublimate. Water, carbon dioxide, carbon monoxide, methane. But the heliocentric distance at which 3I/Atlas begins to show activity is unusually large. Most solar system comets do not develop visible comas until they are within a few astronomical units of the Sun, where temperatures rise above the sublimation points of common ices. But 3I/Atlas shows signs of outgassing while still in the outer solar system, where sunlight is weak and temperatures are frigid. This suggests that the object contains ices more volatile than water, carbon monoxide, perhaps, or nitrogen, which sublimate at much low temperatures. Or it suggests something about the object's structure. If the surface is porous, fluffy, thermally insulating, then even weak sunlight can penetrate and warm subsurface layers where volatile ices reside. Heat does not conduct quickly through loosely packed dust. The object may be insulating itself, trapping solar energy beneath a layer of dust that acts like a blanket, allowing subsurface ices to warm and sublimate even when the surface remains cold. This is how some solar system comets behave, their activity driven not by surface temperature but by subsurface heat transport, by the slow diffusion of warmth through porous material. Only took a few million observations of solar system comets to develop models that might apply here. might not, depending. The dust in the coma scatters sunlight, and the way it scatters depends on the size and shape of the particles. Large particles scatter light differently than small particles. Spherical grains scatter differently than irregular grains. By measuring the colour and polarization of the scattered light, researchers can infer properties of the dust, not precisely, but statistically, in terms of size distributions and refractive indices. The dust from 3a/Atlas appears similar to dust from solar system comets. But there are hints of differences. The colour is slightly redder. Perhaps, or the polarization curves slightly offset. These differences could be meaningful, evidence of composition variations that reflect different formation conditions in a different protoplanetary disk. Or they could be noise, artifacts of the difficulty of measuring faint signals against bright backgrounds. The mystery is not whether the object is active. The images show that it is. The mystery is why it is active where it is, and what that activity reveals about the object's interior. Does it contain pristine ices from its birth system, unchanged over millions of years of interstellar travel? Or has it been altered by cosmic ray bombardment, by collisions with interstellar dust grains, by slow chemical reactions that proceed even at near-zero temperatures over geological timescales? No one knows, and the object is not inclined to explain. The observations continue as the object moves along its trajectory. Ground-based telescopes track it night after night, weather permitting. Space-based telescopes are free from atmospheric turbulence and daylight constraints. Add their data to the growing archive. The Hubble Space Telescope images the object in high resolution, resolving the coma structure, measuring the brightness gradient from the nucleus outward. The data are valuable but limited. Hubble's schedule is oversubscribed. Observing time is allocated in orbits. Each orbit 96 minutes long, only a fraction of which can be spent on any single target. The object moves across the sky, and tracking it requires precise pointing. Frequent updates to the telescope's guidance system. Only took 3 decades of Hubble operations and several $1 billion to build the infrastructure that makes these observations routine. The brightening is not sudden, but gradual, a slow crescendo as the object approaches perihelion, the point in its trajectory closest to the Sun. Perihelion for 3a/Atlas occurs somewhere in the inner solar system. Though still farther out than Earth's orbit, the object does not pass close to any planet. Its trajectory is inclined, elevated above the ecliptic plane, and it moves through relatively empty space. This is fortunate. A close encounter with Jupiter or Saturn would perturb the trajectory, making it difficult to refine the orbit, difficult to study the object's intrinsic properties without the confounding effects of gravitational deflection. The light curve shows peaks and troughs, but also a baseline that rises and falls with heliocentric distance. This is expected. Sunlight intensity decreases with the square of distance, and so does the energy available to sublimate ices and release dust. But the relationship is not perfectly predictable. Comets are not passive reflectors. Their activity depends on thermal inertia, surface properties, the history of past heating and cooling cycles. Some comets brighten faster than expected as they approach the Sun. Some fade slower than expected as they recede. The behaviour depends on details that are difficult to observe and difficult to model. The porosity of the surface, the distribution of ices at different depths, the way dust mantles build up and then blow off. 3a/Atlas follows a curve that is, so far, unremarkable in its broad outlines. It brightens as it approaches. It will fade as it departs. What is remarkable is that it is here at all, a visitor from another star system, carrying information about processes that occurred in a place and time utterly disconnected from human observation, now illuminated briefly by the sun before returning to the dark. Only took chance and geometry and the patience of automated surveys to catch this particular snowflake before it melted back into the void. The spectrum arrives in pieces, different telescopes, different instruments, different nights when the sky is clear and the object is above the horizon. Spectroscopy splits light into its constituent wavelengths, spreading the photons across a detector so that each colour can be measured separately. What emerges is not a smooth rainbow, but a landscape of peaks and valleys. Absorption features where molecules in the coma have stolen specific wavelengths, emission features where excited atoms release energy at characteristic frequencies. These features are fingerprints. They identify what is present in the gas and dust surrounding the nucleus. Water is there. The hydroxyl radical, O, appears in emission, a fragment of water molecules broken apart by ultraviolet sunlight. This is expected. Water ice is ubiquitous in the outer solar system, in comets and icy moons and Kuiper belt objects. But the strength of the hydroxyl emission is weak compared to some solar system comets at similar distances. Either the object is producing less water vapour, or the water is being released in a way that makes it harder to detect, shadowed by dust. Perhaps, or distributed unevenly across the coma. Carbon monoxide shows up in the infrared, a clean double-peaked line that is unmistakable. CO is more volatile than water. It sublimates at temperatures around 25 Kelvin, far colder than the roughly 200 Kelvin needed for water ice to sublimate efficiently. The presence of carbon monoxide explains the early activity. The object is cold enough that water remains frozen, but warm enough, just barely, that carbon monoxide begins to escape. This is the signature of an object that has spent its existence in deep cold, where CO ice can survive without sublimating away over millions of years, only took the width of the universe, more or less, to preserve that ice long enough for it to arrive here. Cyanogen appears faintly. CN, another fragment molecule produced when more complex organic compounds are destroyed by sunlight. Cyanogen is common in solar system comets. It is associated with the breakdown of hydrogen cyanide and other carbon-nitrogen species that may have been incorporated into ices during the object's formation. The presence of CN suggests that the object contains organic material, carbon-rich molecules that formed in the cold outer regions of a protoplanetary disk where carbon monoxide, methane, and other simple molecules could condense onto dust grains and be incorporated into growing planetesimals. The spectrum also shows what is absent. There is no strong signature of methane, though methane should be even more volatile than carbon monoxide. Either methane was never abundant in the object's composition, or it sublimated away long ago during some earlier phase of heating, perhaps when the object was still in its birth system, before it was ejected into interstellar space. Methane ice is fragile. It does not survive long exposure to even weak starlight unless it is buried beneath insulating layers. Only took a few dozen photons per wavelength bin to build this spectrum, each one a lottery win against the noise. The isotopic ratios are harder to measure. Isotopes, atoms of the same element with different numbers of neutrons, have slightly different masses and therefore slightly different spectral features. Deuterium, heavy hydrogen, shifts the wavelengths of molecular lines just enough that, with high-resolution spectroscopy and sufficient signal, the ratio of deuterium to normal hydrogen can be measured. This ratio varies depending on where and how water formed. Water in Earth's oceans has a certain DH ratio. Water in solar system comets has a range of ratios, some similar to Earth's, some much higher. The DH ratio is a tracer of temperature and chemistry during formation. Cold environments tend to produce water with more deuterium, because deuterium-bearing molecules react slightly differently than their lighter counterparts in low-temperature chemistry. For 3I/Atlas, the DH ratio is uncertain, the object is too faint, the spectral lines are too weak. Preliminary measurements suggest a ratio somewhere in the range seen in solar system comets, but the error bars are large. The measurement is consistent with everything and rules out nothing. This is the nature of studying faint objects at great distances. Every number comes with a caveat. Every conclusion is provisional. The carbon isotope ratio, carbon-13 to carbon-12, is similarly elusive. In principle, measuring the isotopic composition of carbon monoxide could reveal details about the chemistry of the protoplanetary disk where the object formed. Different stars have different abundances of heavy elements, depending on their formation history and the generations of stars that came before them. A star that formed from gas enriched by many supernovae will have more heavy elements. More carbon-13, more nitrogen-15. But detecting these subtle shifts requires bright sources and long integrations. 3I/Atlas does not cooperate. Only took a century of quantum mechanics and atomic physics to understand what these lines mean. And still the object keeps most of its secrets. Dust is mixed with the gas. The spectrum shows a broad continuum, smooth emission across many wavelengths, that is the signature of sunlight reflecting off small particles. The shape of the continuum, the way brightness changes with wavelength, provides clues about particle size and composition. Silicate dust, common in solar system comets, produces a characteristic feature around 10 micrometers. A broad emission hump caused by the vibration of silicon-oxygen bonds. For 3I/Atlas, this feature is present but weak, suggesting either that the dust is not dominated by silicates, or that the silicate particles are coated with organic material that dampens the emission. Organic material is dark. It absorbs sunlight across a broad range of wavelengths, giving comets their characteristically low reflectivity. Most cometary nuclei are blacker than coal, reflecting only a few % of the sunlight that strikes them. The darkness comes from complex carbon compounds, tars, tholins, polymerized organics formed by radiation processing of simpler molecules. These materials are not alive, not biological, but they are chemically rich, containing many of the building blocks from which life, elsewhere, might arise. The spectrum of 3I/Atlas, such as it is, resembles solar system comets more than it differs from them. Water, carbon monoxide, cyanogen, silicate dust, organic darkening, all familiar. This is both reassuring and puzzling. Reassuring because it suggests that the chemistry of planet formation may be similar across different star systems, that the same processes that built the solar system's comets operated in the birth system of 3Y/Atlas. Puzzling because it raises the question of what differences, if any, would be detectable. If the object came from a disk around a star with different metallicity, different carbon to oxygen ratio, different temperature structure, how would that show up in the spectrum? And if such differences are present, are the measurements sensitive enough to detect them? Only took a few million CPU hours of radiative transfer modelling to predict what the spectrum should look like. Given various assumptions about composition and structure, there is a feature in the ultraviolet that does not fit easily into the usual catalogue. A faint emission line, possibly from ionised carbon, possibly from a molecular fragment that is not well studied in laboratory spectra. The identification is tentative. Ultraviolet spectroscopy is difficult. Earth's atmosphere absorbs UV light. So these observations must be made from space. And space-based UV spectrographs are rare and precious. The feature could be real, a clue to some unusual chemistry in the object's coma. Or it could be an artifact, a noise spike, a ghost reflection from the instrument's optics. The mystery is not what the spectrum shows, but what it does not show, the missing details, the unresolved lines, the isotopic ratios that are too uncertain to constrain models. The object passes through, and spectroscopy captures a glimpse, a sketch, not a portrait. What remains is the knowledge that somewhere out there, in a protoplanetary disk that will never be observed directly, volatile ices condensed onto dust grains, organic molecules polymerized in the cold and dark, and a small fragment of that disk was ejected into interstellar space where it wandered for ages before the sun's gravity bent its path just enough to carry it within range of Earth's telescopes. Only took the patience of the universe, and a bit of luck, to arrange this fleeting intersection of trajectories. The outgassing should not be happening. Not here. Not at this distance from the sun. Not with the intensity that is observed. Water ice sublimates efficiently only when surface temperatures rise above roughly 200 Kelvin. At the heliocentric distance where 3 I/Atlas first shows activity, beyond 5 astronomical units, farther than Jupiter's orbit, the equilibrium temperature of a dark, slowly rotating body is much colder, perhaps 120 Kelvin, perhaps less. Water should remain frozen, the surface should be inert, and yet the object releases gas and dust, builds a coma, scatters sunlight in ways that indicate material is lifting off the nucleus and spreading into space. Carbon monoxide can explain some of this. CO ice sublimates at much lower temperatures, around 25 Kelvin, even in the outer solar system, even in the faint sunlight beyond Jupiter. Surface temperatures can rise high enough during the day to drive CO sublimation, but the amount of activity observed seems too large to be explained by carbon monoxide alone. The dust production rate, estimated from the brightness and extent of the coma, suggests that substantial mass is being lost. Dust does not sublimate. Dust must be dragged along by escaping gas, entrained in the flow, lifted by the pressure of vapour expanding from beneath the surface. Only took a few algebraic steps to realise the energy budget does not quite close, that something is missing from the accounting. One possibility is that the object's surface is darker than expected, darker even than typical cometary material. A blacker surface absorbs sunlight more efficiently, converts more of the incoming energy into heat rather than reflecting it back into space. If the nucleus is covered with an ultra-dark lag, a crust of dust and organics left behind as ices sublimate, then even weak sunlight could raise surface temperatures higher than equilibrium models predict. Dark surfaces heat quickly. They also cool quickly when the sun sets. But in the hours of daylight, they can reach temperatures tens of degrees warmer than a more reflective surface at the same distance. Another possibility is subsurface activity. If the surface is insulating, porous, low thermal conductivity, then heat absorbed during the day penetrates slowly downward. Warming layers beneath the crust where volatile ices reside, these subsurface ices can sublimate even when the surface itself is cold. The vapour produced diffuses upward through the porous material, finding pathways through cracks and voids, eventually breaking through to the surface where it erupts as jets or diffuse outgassing. This process can continue even at night, fed by heat stored in subsurface layers during the day. The thermal inertia of porous material is low, but not zero. Some heat persists, some sublimation continues in darkness. Only took decades of modelling Comet Halley and Comet Hale-Bopp to understand how comets can be active on their night sides, how thermal waves propagate through dusty ice. The dust itself may play a role. When gas sublimates and escapes, it drags dust particles with it, but only particles small enough and loosely bound enough to be lifted by the gas flow. Larger particles remain behind. Over time, a mantle of dust builds up on the surface, a layer that insulates the ice beneath and reduces further sublimation. But the mantle is fragile. Thermal stresses can crack it. Fresh impacts, micrometeoroids striking the surface, can puncture it. The object's own rotation can cause the mantle to slump or collapse in places, exposing fresh ice that then sublimates vigorously until a new mantle forms. The outgassing from 3/Atlas is not uniform. Images show that the coma is brighter on one side, asymmetric, suggesting that activity is concentrated in certain regions. This is common among solar system comets. Active areas tend to be localized, perhaps at the poles, where seasonal heating is most intense, or at the equator, where sunlight strikes most directly, or perhaps at sites where the crust is thinner, where impacts or previous outbursts have removed the insulating layers. The rotation of the nucleus carries these active regions in and out of sunlight, modulating the activity, creating pulses of a gas and dust that spread into the coma and are then swept back by solar radiation pressure and the solar wind. Only took a few rotations of the object to smear the outbursting into a quasi-steady cloud, smoothing the pulses into something that looks continuous from a distance. Solar radiation pressure pushes on the dust. Photons carry momentum, and when they are absorbed or scattered by dust particles, that momentum is transferred. Small particles, micron-sized grains, are pushed more effectively than large particles. The force depends on the cross-sectional area of the particle, which scales with the square of its size. But the mass scales with the cube. Smaller particles have more area relative to their mass, and so they are accelerated more strongly away from the Sun. The result is that the dust in the coma separates by size. The smallest particles are blown outward rapidly, forming a long tail that points away from the Sun. Larger particles are pushed more gently and fall behind, trailing the nucleus in its orbit. The tail of 3I/Atlas is faint, not the dramatic streamer that some comets produce, but it is there, visible in deep images as a diffuse extension of the coma that stretches in the anti-sunward direction. The length of the tail, and the gradient of brightness along it, can be used to estimate the dust production rate and the distribution of particle sizes. Models suggest that the dust is dominated by particles in the 10 to 100 micron range, large enough to carry significant mass but small enough to be lifted by outgassing. This is consistent with the dust from solar system comets. Another point of resemblance that makes the object seem less alien, more familiar. But the timing of the activity is wrong. Most solar system comets brighten steeply as they approach the Sun, their activity increasing exponentially with decreasing heliocentric distances. Temperatures rise and sublimation accelerates. 3I/Atlas brightens more slowly, its activity beginning farther out and increasing more gradually. This could mean that the object's ice is distributed differently, perhaps more uniformly mixed with dust, so that as surface layers sublimate away, fresh ice is continually exposed. Or it could mean that the object is in the process of disintegrating, that structural failure is occurring, that cracks and fractures are opening up and exposing interior material that has not been processed by previous passes near a star. Only took one close approach to the Sun to find out whether the object would survive. And that approach is still ahead. The non-gravitational forces are subtle but measurable. When a comet outgasses, the escaping vapour exerts a reaction force on the nucleus, a rocket effect. If the outgassing is asymmetric, concentrated on one side of the nucleus, the reaction force has a net direction, pushing the nucleus slightly off the trajectory it would follow under gravity alone. These non-gravitational accelerations are small, typically a fraction of a percent of the Sun's gravitational pull, but they accumulate over time. Astrometric measurements, precise measurements of the object's position on the sky, can detect these deviations and allow the non-gravitational forces to be estimated. For 3I/Atlas, the astrometry shows a deviation consistent with outgassing. The object is accelerating very slightly, in a direction that is not purely radial from the Sun. The magnitude of the acceleration depends on the outgassing rate, the direction of the jets, and the mass of the nucleus. The mass is not known precisely. Estimates are based on the object's brightness and assumptions about its reflectivity and density, but these assumptions are uncertain. A small, bright nucleus produces the same brightness as a large, dark nucleus. A dense, rocky nucleus has more mass than a fluffy, porous nucleus of the same size. The uncertainty compounds. The outgassing rate depends on the mass, and the mass is inferred from the outgassing and brightness. And the brightness depends on the size and reflectivity, and all of these are entangled in ways that make unique solutions elusive. What remains is a range of possibilities, a family of models that fit the data equally well within the noise. The object might be a few hundred meters across, or a few kilometers. It might be losing tons of material per second, or hundreds of kilograms. It might survive its passage through the inner solar system intact, or it might fragment into a debris field that disperses over subsequent orbits, except that there will be no subsequent orbits, because the object's trajectory is unbound, because it will leave the solar system and never return. Only took a few measurements and a lot of algebra to realise how much is still unknown, how fragile the conclusions are, how easy it is to mistake noise for signal and signal for certainty. The trajectory does not close. This is the fundamental fact, the defining characteristic, the reason the object is designated I for interstellar in orbital mechanics. Bound orbits have eccentricities less than 1, ellipses, circles, paths that curve around the Sun and return. Unbound orbits have eccentricities equal to or greater than 1, parabolas and hyperbolas, paths that arrive from infinity and depart to infinity, passing through the solar system once and never again. The eccentricity of 3/8less is measured at approximately 1.3, comfortably hyperbolic, comfortably unbound. But the measurement is not simple. Gravity alone would produce a clean hyperbola, a curve determined entirely by the object's velocity and the Sun's mass. But the object is outgassing, and outgassing produces forces that perturb the trajectory. These non-gravitational forces are small, but they are not negligible. Over weeks and months, as the object moves through the inner solar system, the cumulative effect of outgassing can shift the trajectory by measurable amounts. The challenge is to disentangle the gravitational motion from the non-gravitational perturbations, to determine what the orbit would have been in the absence of activity. Only took several hundred astrometric measurements, taken over months, to refine the orbit enough to detect the non-gravitational component with confidence. The non-gravitational acceleration is directed mostly radially outward from the Sun, but with a component perpendicular to the radial direction. This is the signature of the rocket effect, gas escaping from the sunlit side of the nucleus, producing a thrust that pushes the object slightly away from the Sun and slightly forward in its orbit. The magnitude of the acceleration is consistent with the observed outgassing rate, given reasonable assumptions about the efficiency with which vapour can drag the nucleus along. But there is ambiguity. The direction of the jets, the rotation state of the nucleus, the distribution of active areas, all of these affect how the reaction force is oriented relative to the object's velocity. If the object is tumbling chaotically, the direction of the thrust changes as the nucleus rotates, and the net acceleration averages over the tumbling period. If the object is in a more regular spin state, the thrust may be more consistent, producing a steady acceleration in a fixed direction relative to the orbit. The data are not good enough to distinguish these cases. What is measured is the time average acceleration over weeks, a net effect that could arise from many different rotation geometries. The acceleration affects the object's future trajectory. Without outgassing, the object's velocity at infinity, the speed it will have after escaping the Sun's gravity completely, would be determined by energy conservation. But outgassing adds energy. The rocket effect increases the object's velocity, boosting it slightly as it climbs out of the Sun's gravitational well. The magnitude of this boost depends on how long the outgassing continues, how strong it is, and in what direction the jets are oriented. If the outgassing continues all the way to perihelion and beyond, the boost could be significant. If the outgassing shuts off as the object recedes from the Sun, the boost will be smaller. Only took one pass through the inner solar system to turn a slow interstellar traveller into a slightly faster interstellar traveller, courtesy of the Sun's warmth and the object's own volatility. The rotation complicates everything. A non-rotating nucleus would experience a simple radial thrust, always pointing away from the Sun, but a rotating nucleus presents different faces to the Sun as it spins, and if those faces have different levels of activity, the thrust direction rotates as well. The result is a time-varying force that, when averaged over many rotations, may not point purely radially. This is how some solar system comets develop orbital perturbations that are difficult to model. Their outgassing patterns are complex, the rotation states are not well constrained, and the coupling between rotation and thrust produces accelerations that do not follow simple rules. For 3I/Atlas, the rotation period is uncertain. The light curve suggests a period somewhere between hours and days. but the exact value is difficult to pin down because the brightness variations are not perfectly periodic. The tumbling may be complex, the object wobbling on multiple axes, its orientation changing in ways that are predictable in principle but chaotic in practice. Or the brightness variations may be driven partly by changes in outgassing, by active regions that turn on and off as surface conditions change, by dust clouds that temporarily obscure parts of the nucleus. Only took a few dozen attempts at light curve modelling, each one producing a marginally acceptable fit and wildly different rotation parameters, to realise that the data do not uniquely constrain the spin state. The perturbations propagate forward in time. When the orbit is extrapolated into the future, the uncertainties grow. The object's position a year from now depends on its current velocity, and the velocity depends on the acceleration, and the acceleration depends on the outgassing, and the outgassing may change as the object warms and cools. Small errors in measuring the current acceleration become large errors in predicting the future position. After a few years, the uncertainty in the object's trajectory will be larger than the object itself. After a few centuries, the uncertainty will span a significant fraction of the solar system's width. This is acceptable. The object is leaving. Its future interactions with the solar system are nil. There are no planets in its path, no asteroids to collide with, no spacecraft to avoid. The trajectory after departure is interesting scientifically. It tells where the object is going, which direction in the galaxy it will travel, which stars it might pass near in the distant future. But it has no practical consequences. The object will fade from view as it recedes, becoming too faint to detect within months or years, and after that it will be gone, a data point in the archive, a set of images and spectra that future astronomers may revisit when better models are developed or when similar objects are discovered. The comparison to Oumuamua is inevitable. The first interstellar object, 1I/Oumuamua, also exhibited non-gravitational acceleration, a deviation from a purely gravitational trajectory that sparked extensive debate. Oumuamua showed no visible coma, no obvious outgassing, yet it accelerated as if it were outgassing. Various explanations were proposed: hydrogen icebergs, nitrogen icebergs, low-density fluffy structures, even speculative ideas involving artificial origins. The acceleration was small but statistically significant, and it could not be easily explained by conventional cometary activity, because no conventional cometary activity was observed. Only took one weird object to generate 100 papers and a decade of arguments about what exactly causes interstellar objects to deviate from Keplerian orbits. 3I/Atlas is more conventional. It outgasses visibly. It has a coma, a tail, spectral signatures of volatile release. The non-gravitational acceleration it experiences is consistent with the rocket effect expected from observed outgassing. There is no mystery here, no need for exotic explanations. The object is a comet. It behaves like a comet. It happens to be a comet from another star system. But in most respects it resembles comets from this star system. And that resemblance is itself informative. It suggests that the processes of comet formation are not unique to the solar system, that icy planetesimals are a common outcome of planet formation, that the volatile chemistry seen here is seen elsewhere, but the resemblance also raises the question of how much diversity exists among interstellar objects. Oumuamua was strange. 2I/Borisov was conventional. 3I/Atlas is somewhere in between, mostly conventional, but with quirks, with early activity and unusual outgassing distances and a rotation state that is not easily modelled. As more interstellar objects are discovered, the population will become clearer. Some will be icy, some rocky, some will outgas, some will remain inert, some will be fragments of larger bodies, broken apart by collisions or tidal disruption, some will be pristine, preserved into the cold of interstellar space, carrying information about their birth systems that has not been erased by subsequent processing. Only took 3 confirmed interstellar objects to realise that the sample size is still far too small to draw general conclusions, that every object teaches something but no object is representative. The question of what the object is made of circles back to where it formed. Protoplanetary disks, the swirling clouds of gas and dust that surround young stars and from which planets coalesce, are not uniform. Temperature gradients shape composition. Close to the star, where temperatures exceed several hundred Kelvin, only refractory materials can condense. Silicates, metals, oxides, volatile substances remain gaseous. Farther out, beyond a certain distance called the snowline, temperatures drop below the sublimation point of water ice. Water condenses onto dust grains, dramatically increasing the solid mass available for planet building. Farther still, beyond the carbon monoxide snowline, even more volatile ices condense. See about methane, nitrogen. The composition of a planetesimal reflects the temperature at which it formed. Objects that accreted inside the water snowline are dry, rocky, depleted in volatiles. Objects that formed beyond the snowline are ice-rich, volatile-rich, capable of releasing gas when warmed. The solar system preserves this gradient. Asteroids in the inner belt are dry. Objects in the outer belt show signs of water. Comets from the Kuiper belt and Oort cloud are dominated by ices. The chemistry is not perfectly stratified. Impacts and orbital migration shuffle material, delivering water-rich asteroids to the inner solar system and ejecting icy bodies to the outer reaches. But the overall pattern holds. Only took a few decades of meteorite analysis and spacecraft missions to map the compositional gradient across the solar system and infer its origins in the temperature structure of the protoplanetary disk. 3I/Atlas formed in a disk around another star. The temperature structure of that disk depended on the star's luminosity, the disk's mass, the efficiency of viscous heating, the opacity of the dust. A more luminous star would push the snow lines farther out. A less massive disk would cool more quickly, allowing volatiles to condense closer in. The details are sensitive, but the broad principles are the same. Somewhere in that distant disk, in a region cold enough for carbon monoxide to condense but perhaps not cold enough for nitrogen or methane, dust grains stuck together, volatile ices accumulated, and a small body grew through accretion and collision. The object's composition, water, carbon monoxide, cyanogen, silicate dust, organic material, suggests formation in the outer regions of its birth disk, beyond the CO snowline, in conditions similar to those that produce solar system comets. This is not surprising. Comets are thought to form in the cold outer parts of protoplanetary disks, where temperatures are low and ices are stable. What is perhaps surprising is how similar the composition is. Water and CO are expected. They're abundant throughout the galaxy. Products of oxygen and carbon chemistry that should occur wherever those elements are present. But the ratios, the isotopic signatures, the mix of other species, these could vary depending on the disk's chemical environment. The solar system's composition reflects the composition of the molecular cloud from which the Sun formed, enriched by previous generations of stars that synthesized heavy elements and scattered them into the interstellar medium. Different stars form from clouds with different enrichment histories. A star that formed from material enriched by many Type II supernovae will have more oxygen relative to carbon. A star that formed in a region with significant contributions from Type Ia supernovae will have more iron. These variations, though small, propagate through the chemistry of the protoplanetary disk and into the composition of the objects that form there. Only took billions of years of stellar nuclear synthesis and the deaths of countless massive stars to produce the particular mix of elements that went into making the solar system, and some other mix that went into making the system where 3I/Atlas formed. Measuring these differences requires precision that is difficult to achieve for faint, distant objects, isotopic ratios, the relative abundances of deuterium and hydrogen, carbon-13 and carbon-12, oxygen-18 and oxygen-16 are sensitive traces of chemical history. but measuring them requires high-resolution spectroscopy. Bright signals, long integration times. For 3I/Atlas, the spectra are noisy, the lines are weak, the isotopic features are blended with other spectral features, making deconvolution uncertain. What can be said is that the ratios are not wildly different from solar system values, that the object does not appear to come from a star system with dramatically anomalous composition. But not wildly different is not the same as identical. There could be subtle differences, variations of 10 or 20% that would be scientifically significant but are buried in the noise. These differences would encode information about the metallicity of the parent star, the carbon-to-oxygen ratio of the protoplanetary disk, the efficiency of mixing and chemical reactions during planet formation. All of this information is present, in principle, in the molecules and dust grains of the object's coma. In practice, extracting it is difficult. The organic material complicates the picture. Organic molecules, compounds built from carbon, hydrogen, oxygen, nitrogen, form through a variety of pathways. Some are synthesized in the gas phase, through reactions between simple molecules like carbon monoxide, water, and ammonia. Some are produced on the surfaces of dust grains, where molecules can stick and react at low temperatures, shielded from destructive radiation. Some are produced by radiation processing, ultraviolet light, cosmic rays, breaking bonds and recombining atoms into more complex structures. The result is a mixture of compounds, some simple, some complex, some familiar from laboratory chemistry, some exotic. Only took a few million years of grain surface chemistry, and a few more million of radiation processing to produce the organic mixture observed in comets, and presumably in 3I/Atlas. The organics are dark, they absorb light across a broad spectrum, giving the object a low albedo, the fraction of incident sunlight that is reflected. Estimates based on brightness and size suggest an albedo of a few percent, similar to the darkest solar system comets. This darkness is a signature of carbon-rich material, of polymerized organics that have been irradiated and processed until they are nearly black. These materials are chemically inert, resistant to further change, stable over geological timescales. They coat the surface of the nucleus, insulating the ice beneath, controlling the rate at which volatiles escape. The darkness also makes the object difficult to study. A darker surface reflects less light, producing a fainter image. The brightness of an object depends on its size, its albedo, and its distance. For a given brightness, a large dark object and a small bright object are indistinguishable without additional information. The size of 3I/Atlas is uncertain, inferred from models that assume a typical cometary albedo. If the albedo is lower than assumed, the object is larger. If higher, smaller. The uncertainty propagates into estimates of mass, density, outgassing rate, and all quantities derived from them. The dust grains themselves carry information. Each grain is a microcosm of the disk from which it came, a mixture of silicates, organics, perhaps metal inclusions, perhaps ices, layered and compacted during the accretion process. In solar system comets, dust grains collected by spacecraft and returned to Earth have been analysed in extraordinary detail. They reveal that cometary dust is heterogeneous, that individual grains contain subcomponents that formed in different environments and were later assembled. Some grains contain crystalline silicates that formed at high temperatures, suggesting they originated in the hot inner regions of the disk and were transported outward. Some grains contain amorphous silicates that never experienced high temperatures, consistent with formation in the cold outer disk. For 3I/Atlas, no sample return is possible. The object will not be intercepted. No spacecraft will fly close enough to collect dust, to image the nucleus in high resolution, to measure composition in situ. What is known comes entirely from remote sensing, from light, from spectra, from the faint signals that arrive after travelling across astronomical units and being captured by telescopes. The dust grains in the coma scatter sunlight, and the way they scatter encodes information about size, shape, composition, but extracting that information requires modelling, assumptions, comparisons to laboratory data. Only took the combined efforts of decades of laboratory astrophysics, spacecraft missions, and ground-based observations to build the framework that allows faint spectral features to be interpreted as dust grain properties. With all the attendant uncertainties, the object has been tumbling for a very long time. The rotation state, the way the nucleus spins, the orientation of its angular momentum vector, the stability or chaos of its motion indeed carries a history. Small bodies do not rotate randomly. Their spin is determined by the torques that have acted on them over their lifetimes. Collisions impart angular momentum. Tidal interactions with massive bodies can spin objects up or slow them down. Outgassing, if asymmetric, exerts torques that change the rotation rate and orientation over millions of years. These effects accumulate, and the current rotation state is the sum of all past torques for 3I/Atlas. The rotation period is not precisely known, but the light curve suggests hours to days, and the amplitude of the brightness variation suggests an elongated shape. The tumbling is likely complex, not a simple spin around a single axis, but a wobble, a precession, perhaps even chaotic rotation where the angular momentum vector traces a complicated path on the sky. Complex rotation is common among small, irregularly shaped bodies. Once a body is set tumbling by a collision or a strong torque, it tends to remain in that state for a long time. Energy dissipation, internal friction, tidal effects can damp the tumbling over geological timescales, driving the body towards rotation around its shortest axis, the most stable configuration. But for a small, solid body with little internal dissipation, this damping is slow. Only took a few billion rotations, more or less, to reach whatever tumbling state the object is in now, and perhaps a few billion more to damp into something simpler, except that the object will likely disintegrate or be destroyed long before that happens. The question is when the tumbling began. If the object was ejected from its birth system by a gravitational encounter, a close pass by a planet or another planetesimal, the encounter itself could have imparted significant angular momentum. Tidal forces during the flyby could have torqued the object, setting it spinning or tumbling. The magnitude of the torque depends on how close the encounter was, how fast the object was moving, how elongated its shape was at the time. If the object passed within a few planetary radii of a giant planet, the tidal torque could have been substantial, enough to induce rapid rotation or even structural damage. Alternatively, the tumbling could have been initiated later, after ejection, during the object's journey through interstellar space. Collisions with interstellar dust grains are rare but not impossible. A grain travelling at typical interstellar velocities, tens of kilometres per second relative to the object, carries significant kinetic energy. A single grain impact does not deliver much angular momentum, but over millions of years, many impacts accumulate. The net effect is a random walk in angular momentum space, slowly changing the object's spin state in unpredictable ways. Radiation pressure from starlight also exerts torques. If the object is not spherical, if its shape is irregular, sunlight striking different parts of the surface produces forces that do not pass through the centre of mass. These offset forces create torques. The effect is small, but over long timescales it is not negligible. The Yorp effect, named after Yukovsky, O'Keefe, Radzievsky, and Paddock, describes how thermal emission can spin up or spin down small asteroids in the solar system. An analogous effect operates in interstellar space, driven not by the sun but by the diffuse starlight of the galaxy. The effect is much weaker, but time is abundant. Only took a few theorists and some careful calculations to show that even the faint glow of distant stars accumulated over millions of years can change an object's spin state measurably. The object's birth system is unknown. The trajectory, when extrapolated backward, points toward a region of sky, but that region contains many stars, and over the millions of years since ejection, both the object and the stars have moved. The Sun orbits the galactic centre at about 220 kilometres per second. Other stars have their own orbital velocities, their own peculiar motions relative to the local standard of rest. Over a few million years, the relative positions of stars change significantly. A star that is currently in the direction from which the object came may not have been in that direction when the object was ejected. The problem of tracing the object's origin requires not just the object's current trajectory, but also the motions of all nearby stars over millions of years. Surveys like Gaia have measured the positions and velocities of over 1 billion stars in the Milky Way. These data allow, in principle, the past motions of stars to be reconstructed by integrating stellar orbits backward in time and comparing them to the integrated trajectory of 3 1/Atlas. It may be possible to identify stars that were close to the object's path in the past. But the uncertainties are large. Small errors in measuring a star's velocity translate into large errors in its position millions of years ago. The object's trajectory is also uncertain, affected by non-gravitational forces that are difficult to model and by potential gravitational perturbations from unseen objects. Rogue planets, brown dwarfs, molecular clouds, encountered during the journey. No definitive parent star has been identified. There are candidates, stars whose past positions, given their measured velocities, place them near the object's backtrack trajectory. But the matches are not unique. Several stars fit the criteria within the uncertainties. The object could have come from any of them, or from a star that is too faint or too distant to have been included in the survey. The origin remains unresolved, a puzzle that may never have a unique solution. Only took the width of a galaxy and a few million years to scramble the evidence so thoroughly that even careful detective work cannot reconstruct the scene. The age of the object is also uncertain. It could be as old as its birth system, just as 4 or 5 billion years, if it formed around a star similar to the Sun, or it could be younger, if it came from a system that formed more recently, or if it was created by a collision that broke apart a larger body. The surface shows no obvious signs of recent formation. There are no fresh impact craters visible in the low-resolution images, no bright patches that might indicate exposed fresh ice. But the resolution is poor. The object is small and distant. Details smaller than a few hundred meters cannot be resolved from Earth. The isotopic composition, if it could be measured precisely, might constrain the age. Radioactive isotopes decay over time, changing the ratios of parent to daughter elements. Aluminum-26, which was present in the early solar system, decays to magnesium-26 with a half-life of about 700,000 years. Objects that formed early in the solar system's history, within the first few million years, contain excess magnesium-26, a signature of the now-decayed aluminum. Objects that formed later do not. Similar traces exist for other isotopes, but detecting these signatures requires laboratory analysis of samples, not remote spectroscopy of a faint coma. The object tumbles, and in its tumbling is encoded a history that is partly legible and partly lost. The rotation rate suggests that the object is not at the threshold of structural failure. It is not spinning so fast that centrifugal forces threaten to tear it apart. The tumbling suggests that the object has experienced torques, impacts, or tidal encounters at some point in its past. The elongated shape suggests that the object is strong enough to maintain an irregular form, that it is not a rubble pile held together only by weak self-gravity. Beyond these general statements, the details dissolve into uncertainty. The object continues to rotate as it moves through the solar system. Each rotation takes hours or days. Each rotation brings different parts of the surface into sunlight, warming them, driving sublimation, releasing gas and dust. The rotation is not slowing detectably, not yet. The torques from outgassing are small compared to the object's angular momentum. Over weeks or months, the spin state may change slightly, but the observations are not precise enough to measure the change. The object spins, and the spinning continues, indifferent to observation, governed by conservation laws that operate the same way here as they do in whatever distant disk the object once called home. Only took a few principles of mechanics, known for centuries, to predict how spinning bodies behave, and yet the specific history of this specific body remains inaccessible, its past hidden behind the noise of measurement and the scrambling of time. The galaxy is not empty. Between the stars, in the vast spaces that dwarf even the distances within solar systems, there is matter, gas, mostly hydrogen, some helium, traces of heavier elements, spreads through the interstellar medium at densities of about 1 atom per cubic centimetre, sometimes less, sometimes more in molecular clouds where new stars are forming. Dust grains, microscopic particles of silicate and carbon, drift through this gas, their surfaces accumulating thin ice mantles of water, carbon monoxide, methane. Depending on local conditions, magnetic fields thread the medium, shaping the flow of charged particles. Cosmic rays, high-energy protons and atomic nuclei accelerated by supernova shocks and other violent processes, permeate everything, ionizing atoms, breaking molecules, depositing energy. An object travelling through interstellar space does not move through a vacuum. It moves through this medium, and the medium acts on it. The drag is negligible. The density is so low that even over millions of years, the object's velocity changes by only a tiny amount. But the interactions are not negligible. Cosmic rays strike the surface, penetrating microns to millimeters depending on their energy. Each impact breaks chemical bonds, displaces atoms, creates defects in crystalline structures. Over time, the surface is damaged, amorphized, its original texture erased and replaced by a radiation-processed layer. Only took a few million years of cosmic ray bombardment to alter the top millimetre or so of the object's surface, turning crystalline ice into amorphous ice, breaking complex molecules into simpler fragments, darkening organics into carbon-rich residues. Interstellar dust grains, though tiny, carry momentum. A grain moving at 30 kilometers per second relative to the object hits with kinetic energy, proportional to the square of that velocity. The energy is deposited in a tiny volume, creating a miniature impact crater, vaporizing a small amount of material, perhaps sputtering atoms off the surface. The erosion rate is slow, nanometers per million years perhaps, but it is not zero. Over the lifetime of the object's journey, the outermost layers of the surface have been sand-blasted away, grain by grain, impact by impact. The ice mantles on interstellar dust grains can stick to the object's surface when they collide, adding material rather than removing it. But the rate of accretion is even slower than the rate of erosion, and the net effect is uncertain. What is certain is that the surface of 3I/Atlas, as it exists now, is not the same surface that existed when the object was ejected from its birth system. The surface has been processed, altered, its composition and structure shaped by the environment through which it has travelled. Gravitational encounters also shape trajectories. A close pass by another star can deflect the object, changing its velocity and direction. The deflection depends on the mass of the star, the distance of closest approach, and the relative velocity. Most encounters are distant, the star passing several light-years away, the gravitational perturbation small, but occasionally due to an object passes closer, within a light-year, within a few tenths of a light-year, and the deflection is significant. Over millions of years, multiple encounters accumulate, and the object's trajectory becomes a random walk, its path shaped by the collective influence of many stars. Only took a few dozen stellar encounters, or a few hundred, or none at all, depending on the object's path and the density of stars along the way, to bend its trajectory from its initial ejection velocity to whatever velocity it had when it entered the solar system. Molecular clouds present a different kind of hazard. These are regions where the interstellar medium is much denser, hundreds or thousands of atoms per cubic centimetre, and much colder, with temperatures around 10 to 20 Kelvin. Molecular clouds are the sites of star formation, dense enough that gravity can overcome thermal pressure and trigger collapse. They are also obstacles. An object passing through a molecular cloud experiences increased drag, a small but measurable deceleration as it ploughs through the denser medium. The cloud's gravity also deflects the object's path, though unless the object passes very close to the cloud's densest regions, the deflection is minor. The time an object spends crossing a molecular cloud is short, thousands of years perhaps, but the interaction leaves marks. The increased flux of dust grains and molecules can erode the surface more rapidly. The lower temperature, if the object is still warm from its birth system, can cause thermal stress, cracking the surface as it cools. Conversely, if the object is already cold, the molecular cloud's environment is not much different from the surrounding interstellar medium, and the passage is uneventful. The object's journey through the galaxy has been long. The ejection velocity from its birth system, the velocity with which it was launched into interstellar space, is not known precisely, but typical ejection velocities for objects expelled by planetary encounters are a few kilometers per second relative to the parent star, added to the star's own velocity relative to the local standard of rest. This gives the object a velocity of perhaps 20 to 30 kilometers per second relative to nearby stars. At that speed, it takes about 100,000 years to travel 1 light year. If the object originated tens or hundreds of light years away, the journey took millions to tens of millions of years. Only took the slow accumulation of distance, kilometre by kilometre, over timescales that human minds struggle to internalise. To cross from there to here, during that journey, the object was in darkness. The light of the nearer stars is faint, too faint to warm the surface appreciably. The equilibrium temperature of a body in interstellar space, far from any star, is determined by the cosmic microwave background, the relic radiation from the Big Bang, now cooled to about 2.7 Kelvin. Objects in interstellar space are slightly warmer than this, perhaps 3 to 5 Kelvin, due to internal heat from radioactive decay and residual warmth from formation. But 3 Kelvin is cold beyond human experience, cold enough that almost all molecular motion ceases, cold enough that even the most volatile ices, hydrogen, helium, are near their freezing points. At these temperatures, sublimation is negligible. The object's volatiles do not escape. The ices are locked in place, preserved as they were when the object left its birth system. This is why interstellar objects are interesting, Marissa. They're time capsules, carrying pristine samples of material from other planetary systems, unprocessed by the sun's heat, uncontaminated by solar system chemistry. The surface may have been altered by radiation and impacts, but the interior, shielded by meters or tens of meters of overlying material, remains unchanged. The darkness also means the object is invisible. There is no sunlight to reflect, no internal activity to produce a coma. The object drifts unseen, undetected, one of countless similar objects that populate the space between stars. Estimates of the density of interstellar objects vary widely, but models suggest there may be trillions of them in the Milky Way. Fragments ejected from planetary systems during their formation or evolution, now scattered through the galaxy. Most of them never illuminated, never observed, never catalogued. Only took the invention of telescopes, and then the invention of sensitive detectors, and then the invention of automated surveys, to begin detecting the tiny fraction of these objects that happen to pass close enough to a star to be visible. The encounter with the solar system is brief. The object's velocity is high enough that it spends only months or years within the region where solar heating is significant, where outgassing occurs, where telescopes can detect it. Before that, it spent millions of years in the cold and dark. After it leaves, it will spend millions more. The illuminated phase, the active phase, the observable phase, all of these are transient, a brief interruption in a longer journey that spans the galaxy. Tidal forces are weak at interstellar distances. Stars are far apart, and unless the object passes very close to one, the differential gravitational pull across its extent is negligible. The object does not deform, does not experience tidal heating, doesn't fragment due to tidal stress during its journey, but when it enters the solar system, the tidal environment changes. The sun's gravity creates a gradient. The near side of the object is pulled more strongly than the far side. For a small object at large distances, this gradient is tiny. But as the object approaches perihelion, the tidal forces increase. Whether those forces are strong enough to matter depends on the object's size, structure, and tensile strength. A solid, monolithic body can withstand significant tidal stress. A rubble pile, a collection of loosely bound fragments held together only by weak gravity, can be torn apart if the tidal forces exceed the gravitational binding. The threshold, called the Roche limit, depends on the densities of the object and the body exerting the tides. For a typical comet passing within the orbit of Mercury, tidal disruption is unlikely unless the object is already fragile, already fractured, already on the verge of coming apart, only took one close pass, or maybe none, to determine whether the object is strong enough to survive, and the answer will be known soon as perihelion approaches. Most interstellar objects are never seen. The solar system is large, but the volume of space through which objects might pass is vastly larger, and most trajectories do not bring objects close enough to the Sun to be detected. An object passing through the outer reaches of the Oort cloud, tens of thousands of astronomical units from the Sun, remains far too faint to be visible even with the most sensitive telescopes. It moves through the Sun's gravitational influence, its path slightly bent by the encounter, but it does not enter the region where reflected sunlight makes it detectable. The detection of interstellar objects is biased towards those that pass close to the Sun and close to Earth. An object that passes through the inner solar system but does so when Earth is on the opposite side of its orbit may not be discovered, or may be discovered only briefly, without enough observations to determine its trajectory accurately. An object that passes through during daylight, or during cloudy weather, or during a time when no survey telescope happens to be pointing in the right direction, is missed entirely. The discovery rate depends not only on how many objects are passing through, but on the coverage and sensitivity of the surveys watching for them. Only took a few decades of increasingly sophisticated sky surveys to begin detecting interstellar objects at a rate of one every few years, and the rate is increasing as survey technology improves. The Asteroid Terrestrial Impact Last Alert System, ATLAS, is one such survey. It consists of multiple telescopes, located in Hawaii and other sites, that repeatedly image the entire visible sky every few nights. The goal is to detect near-Earth asteroids that might pose an impact threat, but the survey also finds comets, distant trans-Neptunian objects, and occasionally interstellar visitors. The survey operates automatically. Images are taken, processed, compared to reference catalogues, and any moving objects are flagged for follow-up. The software does not care whether an object is bound to the Sun or not. It simply reports motion, and humans or other algorithms analyze the motion to determine orbital parameters. The designation process is bureaucratic. When a new object is discovered, it is assigned a provisional designation based on the date of discovery and the order in which it was reported. Observations accumulate. The orbit is refined. If the orbit is determined to be interstellar, eccentricity greater than 1, unambiguously unbound, the object is submitted to the International Astronomical Union for confirmation. The IAU evaluates the data, checks the orbit determination, and if the interstellar nature is confirmed, assigns a permanent designation with the I prefix. For 3I/Atlas, this process took weeks. Early observations suggested an unusual orbit, but the uncertainties were large. Additional observations from multiple sites tightened the constraints, confirmed the hyperbolic trajectory, and the designation followed. The name Atlas is appended to the 3I as a courtesy, acknowledging the survey that discovered the object. There is no deeper meaning. The object is not named after a person or a place or a myth. It is a catalogue entry, functional and unromantic, the kind of label that scales efficiently as the number of known objects grows. The first interstellar object, Oumuamua, was named by its discoverers, who chose a Hawaiian word meaning scout or messenger from the distant past. The second, Borisov, was named after the amateur astronomer who discovered it. The naming conventions are inconsistent, reflecting the ad hoc nature of early interstellar object discoveries. As the population grows, standardized naming schemes will likely replace individual creativity, and objects will be known by their catalogue numbers, their trajectories, their spectral types, rather than by names that evoke narratives or meanings. Only took 3 objects to reveal that humanity's instinct to name things is in tension with the practicalities of cataloguing a population that may eventually number in the hundreds or thousands. The bias in detection shapes the known population. Objects that are bright are easier to detect than objects that are faint. Objects that pass close to Earth are easier to follow up than objects that remain distant. Objects that outgas and develop comas are easier to spot than objects that remain inert. The first 3 confirmed interstellar objects, Oumuamua, Borisov, and Atlas, are not a representative sample. They are the objects that happen to be discovered, and the factors that led to their discovery are not random. Oumuamua was discovered because it passed very close to Earth, within 0.16 astronomical units, and because it was moving quickly, which made it conspicuous against the background of solar system objects. Borisov was discovered while it was still far from the Sun, beyond the orbit of Jupiter, because it developed a coma early and was therefore bright enough to be detected by an amateur astronomer with a modest telescope. Atlas was discovered because it passed through a region of sky being monitored by an automated survey designed to find exactly this kind of object. How many other interstellar objects have passed through undetected? The estimate depends on models of the interstellar object population, their size distribution, their trajectories, and the detection limits of current surveys. Models suggest that for every interstellar object detected, dozens or hundreds pass through undetected. The objects that are missed are mostly small, faint, or on trajectories that do not bring them close to the Sun. Larger objects, which are rarer, are easier to detect at greater distances. Smaller objects, which are more numerous, are detectable only if they pass very close or if they're unusually bright. Only took a bit of statistics and some reasonable assumptions to conclude that the solar system is currently host to several interstellar objects that will never be discovered because they are already outbound and fading, or because they never brightened enough to be visible in the first place. The population of interstellar objects in the galaxy is enormous. Every star system with planets likely ejects material during its formation and evolution. Giant planets, as they migrate or scatter each other, fling smaller bodies out of the system. Collisions between planets or planetesimals produce fragments that can be ejected if the impact velocity is high enough. Close stellar encounters can perturb the outer regions of a planetary system, sending comets and asteroids into the interstellar medium. Over billions of years, each star system contributes a reservoir of material to the galaxy's inventory of unbound objects. The ejection rate is uncertain, but estimates based on solar system dynamics suggest that for every star, tens of Earth masses of material may be ejected over the lifetime of the planetary system. Most of this mass is in the form of small bodies, comets, asteroids, planetesimals, rather than planets. The total mass of interstellar objects in the Milky Way summed over all stars is staggering. Though the density is low, the average separation between interstellar objects is large, measured in millions of kilometers or more, so encounters between them are rare. The objects drift. Their velocities relative to the local standard of rest are typically a few tens of kilometers per second. They're not bound to any star, but they're bound to the galaxy as a whole, orbiting the galactic center along with the stars. Gas and dust Their orbits are influenced by the galaxy's gravitational potential, the combined pull of the disk, the bulge, the dark matter halo. Over hundreds of millions of years, their orbits precess, their eccentricities evolve, their inclinations change. The galaxy stirs them slowly, mixing them through its volume, redistributing them without destroying them. Only took the mass of a few 100 billion stars and the dark matter that binds them to create a gravitational field strong enough to keep even the most wayward objects from escaping into intergalactic space. Some interstellar objects are captured. If an object passes close to a star at just the right velocity and angle, the star's gravity can bend the trajectory into a closed orbit, trapping the object. The probability of capture is low. Most encounters result in deflection, not capture, but over the history of the solar system. Some interstellar objects may have been captured and now orbit the Sun indistinguishably from native objects. Identifying captured interstellar objects is difficult. They have had billions of years to be perturbed by planets, to collide with other objects, to have their orbits reshaped. There are no obvious markers that distinguish a captured interstellar object from a native one. Some candidates have been proposed. Certain outer solar system objects have unusual orbits, high inclinations, retrograde motion, extreme eccentricities that are difficult to explain through standard solar system formation models. These could be captured interstellar objects, or they could be native objects that were scattered into unusual orbits by gravitational interactions. Distinguishing between these possibilities requires detailed dynamical modelling and, ideally, compositional measurements that might reveal differences between interstellar and solar material. 3I/Atlas will not be captured. Its velocity is too high, its trajectory too steep. It will pass through, bend slightly under the Sun's gravity, and depart. The encounter is gravitationally insignificant from the object's perspective. The Sun is simply another star along its path, one that happens to be close enough and bright enough to warm the surface briefly and make the object visible. The object does not care. It has been travelling for millions of years and will continue to travel for millions more. Indifferent to this brief moment of illumination, only took the alignment of trajectories and the timing of surveys to ensure that this particular object, among countless others, would be seen and recorded and analysed before it vanished back into the dark from which it came. The three confirmed interstellar objects are not alike. Oumuamua, the first, was peculiar in almost every way. Its shape, inferred from the large amplitude of its light curve, was elongated, perhaps 10:1 in its longest to shortest dimension, more elongated than any known solar system asteroid or comet. Its surface was red, but not as red as typical outer solar system objects. It showed no coma, no visible outgassing, yet its trajectory exhibited non-gravitational acceleration consistent with a cometary outgassing force. Attempts to detect gas emission failed. No water, no carbon monoxide, no cyanogen, nothing. The object was either outgassing something that was invisible to the instruments used, or the acceleration was caused by some other mechanism. The debate over Oumuamua's nature generated numerous papers. Some proposed that the object was a hydrogen iceberg, a fragment of a molecular cloud frozen into solid hydrogen, which would sublimate invisibly and produce the observed acceleration. Others suggested nitrogen ice, analogous to the surface of Pluto, which also sublimates without producing detectable gas emission. Still others invoked mechanisms like radiation pressure on a thin, light sail-like structure, a hypothesis that veered into speculation about artificial origins. Though most astronomers regarded this as implausible, only took one weird object to demonstrate how much is still unknown about what interstellar objects can be, and how difficult it is to draw conclusions from limited data. 2I/Borisov, the second interstellar object, was conventional. It developed a coma when it was still far from the Sun, showed clear spectroscopic signatures of water and carbon monoxide, and behaved like a typical solar system comet in almost every measurable way. Its colour was slightly redder than average, but within the range seen in solar system comets, its dust production rate, its gas-to-dust ratio, its coma morphology, all familiar. The only remarkable thing about Borisov was that it was not from the solar system. Its trajectory was hyperbolic, its origin extrasolar, but its composition and behaviour were so similar to solar system comets that it could have passed unnoticed if not for the orbital determination. Borisov's conventionality was, in its own way, informative. It suggested that the processes that form icy bodies in the outer regions of protoplanetary disks are robust, that they produce similar results regardless of the specifics of the parent star. Water and carbon monoxide are abundant molecules, and their presence in Borisov indicated that the chemistry of its birth disk was not radically different from the chemistry of the solar nebula. The object fit expectations. It was reassuring, unremarkable, a confirmation that not all interstellar objects would be as strange as Oumuamua. 3I/Atlas falls somewhere in between. It outgasses, like Borisov, but its activity begins unusually far from the Sun, suggesting high volatile content or unusual structure. Its tumbling and elongated shape are reminiscent of Oumuamua, but not as extreme. Its spectrum shows familiar molecules. Water, carbon monoxide, cyanogen, but with some hints of differences in the ratios and the strength of emission. The object is not deeply strange, but it is not entirely conventional either. It occupies a middle ground, a reminder that the population of interstellar objects is likely diverse, that no single example is representative. Only took 3 objects to reveal that the term interstellar object encompasses a range of types, and that generalizing from a sample size of 3 is hazardous. The diversity may reflect different formation environments. Borisov-like objects, icy and volatile rich, probably formed in the cold outer regions of their birth disks, beyond the CO snowline, where temperatures were low enough for even the most volatile species to condense. Oumuamua-like objects, if they are hydrogen or nitrogen icebergs, might have formed in even colder environments, perhaps in the outermost reaches of a protoplanetary disk, or in regions of molecular clouds where temperatures approach 10 Kelvin. Alternatively, Oumuamua might be a fragment of a larger body, broken apart by collision, its unusual shape a result of the fracture rather than accretion. 3I/Atlas, with its mix of properties, might represent a common type, objects that are ice-rich but not primordially pristine, that have experienced some degree of thermal or collisional processing, that were ejected from intermediate regions of their birth disks where temperatures were cold but not the coldest. Or it might be a transitional object, caught between states, in the process of evolving from one type to another as sublimation erodes its surface and changes its composition. The rotation states also differ. Oumuamua was tumbling, though the exact rotation period was debated. Borisov appeared to be rotating more regularly, with a period of hours and less complex tumbling. 3I/Atlas tumbles, but the period and geometry are not well constrained. These differences might reflect different collisional histories, different ejection mechanisms, different torques experienced during the journey through interstellar space. Or they might be stochastic, random outcomes of chaotic processes that do not follow predictable patterns. The outgassing behaviour varies. Oumuamua did not outgas visibly, or if it did, the emission was too faint to detect. Borisov outgassed strongly, with a well-developed coma and tail, 3I/Atlas outgasses at an intermediate level, producing a coma but not a dramatic tail, active at large distances but not as dramatically active as some solar system comets at similar distances. These variations suggest different volatile inventories, different surface properties, different thermal structures. An object with abundant near-surface volatiles outgasses more readily. An object with a thick insulating crust outgasses less, or only after the crust is breached. Only took a handful of observations and a few clever models to sketch the outlines of these differences. But the details remain elusive, hidden behind the noise and the limitations of remote sensing. Comparing interstellar objects to solar system comets also reveals differences. Solar system comets come in two main populations: Jupiter family comets, which have relatively short orbital periods and low inclinations, originating mostly from the Kuiper belt, and long-period comets, which have very long orbital periods and random inclinations, originating from the Oort cloud. The compositions of these populations differ slightly. Jupiter family comets tend to have less carbon monoxide relative to water, perhaps because they formed in warmer regions or have been processed more by repeated passages near the Sun. Long-period comets, making their first or second passage through the inner solar system, retain more pristine compositions. Interstellar objects are, in some sense, the ultimate long-period comets. They have never been heated by the Sun until their current passage. Their compositions should be pristine, unmodified by solar processing, but they may have been modified by their birth stars, by the conditions in their birth disks, by processes that occurred before ejection. The comparison is not straightforward. An interstellar object from a young, hot star might have a very different composition than an object from an old, cool star. An object ejected early in its system's history might differ from one ejected later. After planets had formed and migrated, the sample size is too small to draw firm conclusions. 3 objects do not define a population. Statistical studies require tens or hundreds of examples, enough to map out the range of properties, to identify correlations, to test models of formation and evolution. Current surveys are detecting interstellar objects at a rate of roughly 1 per year, a rate that will increase as new telescopes come online. The Vera Rubin Observatory, scheduled to begin operations soon, will survey the sky far more comprehensively than current surveys, and is expected to detect dozens of interstellar objects per year. Only took a few centuries of astronomy and a few decades of automated sky surveys to reach the point where interstellar objects transition from rare curiosities to a population that can be studied statistically. When the sample is larger, patterns will emerge. Some objects will be icy, some rocky, some will be fragments, some intact. Some will show signs of recent activity, others ancient dormancy. The distribution of sizes, shapes, compositions, rotation states, and trajectories will reveal how planetary systems form and evolve, how material is ejected, how it survives the journey through interstellar space. Each object is a data point, a sample from a protoplanetary disk that cannot be observed directly, a messenger carrying information across light years and millions of years. 3I/Atlas is one such messenger. It carries information about the disk where it formed, about the star that warmed it in its youth, about the processes that ejected it and the environment through which it travelled. The information is encoded in its composition, its structure, its rotation, its outgassing. Decoding the information requires observations, models, comparisons, patience. Some of the information can be extracted now, some will require better instruments, longer observations, closer encounters. Some may remain inaccessible, lost to the limitations of remote sensing and the passage of time. Only took the convergence of this object's trajectory with the solar system's position, at this moment in time, to make any of this possible, a fleeting opportunity to study something that came from elsewhere, that will soon return to elsewhere, and that offers a glimpse into the diversity of worlds beyond the Sun's domain. Perihelion approaches. This is the point of closest approach to the Sun, the moment when solar heating is strongest, when outgassing reaches its peak, when the object is most visible and most vulnerable. For 3I/Atlas, perihelion occurs at a distance of approximately 2 astronomical units, roughly the orbital distance of Mars. Farther in than the asteroid belt, but not as close as Earth. At this distance, the Sun is bright, but not overwhelmingly so. The equilibrium temperature of a dark, slowly rotating body at 2 astronomical units is around 200 Kelvin. Cold by terrestrial standards, but warm enough to drive substantial sublimation of water ice. The object has been warming for weeks. As it descends toward perihelion, the intensity of sunlight increases inversely with the square of the distance. Closer means brighter, and brighter means warmer. The warming is not instantaneous. Thermal energy takes time to penetrate the surface and diffuse inward. A porous, insulating crust slows the penetration, creating a thermal lag between the surface and the subsurface. The surface warms quickly during the day and cools quickly at night, but the layers beneath remain more stable, their temperature rising gradually as heat accumulates over days and weeks. Only took a few months of steady heating to raise the subsurface temperature high enough that water ice begins to sublimate efficiently. Adding water vapour to the carbon monoxide that has been outgassing since farther out, the outgassing intensifies. More gas escapes, dragging more dust with it. The coma brightens and expands, the tail lengthens. Observers on Earth see the object's brightness increase faster than the inverse square law alone would predict. This is the signature of increasing activity, of sublimation that accelerates as temperatures rise. The dust production rate, estimated from the coma's brightness and the scattering properties of the dust, climbs from kilograms per second to tens of kilograms per second, perhaps more. The dust is a problem for the nucleus. As volatile ices sublimate, they leave behind non-volatile material, silicate dust, organic grains, refractory particles that do not sublimate at cometary temperatures. This material accumulates on the surface, forming a lag deposit, a crust that insulates the ice beneath and reduces further sublimation. The formation of a dust mantle is a self-limiting process. As the mantle thickens, sublimation slows, the coma fades, and the object becomes less active. But the mantle is fragile. Thermal stress can crack it. Gas pressure building up beneath it can blow it off in localized outbursts. The object's rotation causes the mantle to shift and slump, exposing fresh ice. The activity may not be uniform. Some regions of the surface may be more active than others, producing jets that are brighter and more collimated than the diffuse outgassing from the rest of the nucleus. Jets are common in solar system comets. They're caused by localized sources of sublimation, fractures in the crust, thin spots in the mantle, regions where the ice is closer to the surface. As the nucleus rotates, these active areas move in and out of sunlight, and the jets turn on and off, creating variability in the coma's brightness and structure. Only took a few dozen images taken hours apart to reveal hints of asymmetry in the coma, suggestions that the outgassing is not perfectly symmetric, that jets or active regions are present, though resolving their exact locations and orientations is beyond the capability of current observations. The tidal forces at perihelion are weak but not negligible. The sun's gravity creates a gradient across the object. The near side is pulled slightly more strongly than the far side. For a small object with low tensile strength, this differential pull can cause stress. If the object is a rubble pile, a collection of loosely bound fragments held together only by weak gravity, the tidal forces might overcome the gravitational binding and pull the object apart. This is how some comets fragment as they approach the Sun, not from heating alone, but from the combination of thermal stress and tidal stress. For a solid, coherent nucleus, tidal disruption at 2 astronomical units is unlikely. The tidal force is not strong enough to overcome the mechanical strength of rock and ice. But if the object is already fractured, already weakened by thermal cycling or previous impacts, the tidal stress could exploit existing cracks and cause the object to split. The outcome depends on the object's internal structure, which is not known. Thermal stress is a more plausible mechanism for fragmentation. As the surface warms, it expands. As it cools, it contracts. The mismatch between the warm surface and the cold interior creates stress. Materials with different thermal expansion coefficients, ice and rock, for example, expand and contract at different rates, creating additional stress at their interfaces. Over many heating and cooling cycles, cracks form and propagate. Eventually, the nucleus may split along these cracks, breaking into 2 or more fragments that then follow slightly different orbits. Fragmentation is common among comets. Many comets have been observed to split, either suddenly or gradually, as they approach the Sun, Some splits are triggered by outbursts, sudden releases of gas and dust that exert forces strong enough to break the nucleus apart. Some splits occur more quietly, the nucleus simply coming apart without dramatic activity. The fragments, once separated, follow diverging paths, their orbits perturbed by the different levels of outgassing each experiences. Only took one observation of a split nucleus, seen in hindsight in images taken days apart, to confirm that comets are not always structurally robust, that they can disintegrate even without dramatic collisions or extreme solar heating. For 3I/Atlas, the possibility of fragmentation is real but not certain. The object is small, perhaps a few hundred meters to a kilometer across, and small objects have less gravitational binding energy. The surface-to-volume ratio is high, meaning that thermal stresses penetrate more deeply relative to the size of the object. If the object is monolithic, a single solid piece, it might survive. If it is a rubble pile or a weakly bound aggregate, it might not. The observations do not yet show signs of fragmentation. The light curve remains consistent with a single nucleus, not multiple fragments. The coma is more or less symmetric, not elongated in the way that would suggest material streaming from two separating pieces. But fragmentation, if it occurs, might not be immediately obvious. The fragments might remain close together, their relative velocity small, so that they appear as a single unresolved object in images. Only over days or weeks, as the fragments drift apart, would the split become detectable. Observers continue to monitor. Images are taken nightly, weather permitting. The object's brightness, position, and coma morphology are recorded. Any sudden changes, a brightening that is too rapid, an asymmetry that appears or intensifies, a doubling of the light curve period that might indicate a split, will be noted and analysed. The object does not narrate its own story, but it provides clues, and the clues accumulate. The mystery, as perihelion approaches, is whether the object will survive intact or whether the stress of heating, tidal forces, and outgassing will cause it to fragment. Both outcomes are plausible. Both have precedence among solar system comets. The object, oblivious to speculation, continues its approach, warming, outgassing, spinning, shaped by forces that have operated for millions of years and will continue to operate regardless of whether anyone's watching. Only took the alignment of Earth's position and the object's trajectory to place the moment of perihelion within optimal observing geometry, so that telescopes can watch as the object reaches its closest, warmest, most active point before beginning the long fade into the outer solar system and beyond. The dust tells a story, though the language is subtle. Each particle released from the nucleus carries information about the conditions under which it was liberated. Large particles, tens to hundreds of microns across, are difficult to lift. They require strong gas flow, high sublimation rates, or particularly vigorous jets. Small particles, micron-sized or smaller, are lifted more easily. They're swept up by even gentle outgassing, carried into the coma where solar radiation pressure pushes them into the tail. The distribution of particle sizes, how many large particles relative to small, how the distribution is shaped, depends on the structure of the surface material, the way dust is bound to ice, the strength of the cohesive forces that hold grains together. Observations of the dust coma, analysed through models that account for how particles of different sizes scatter sunlight, suggest that 3I/Atlas is producing a broad range of particle sizes. The coma is brightest near the nucleus, where both large and small particles contribute to the scattered light, and it fades gradually outward as the smallest particles are preferentially pushed away by radiation pressure. The tail, when resolved in deep images, shows gradation, brighter near the nucleus, fainter and more diffuse farther out. This gradient encodes the particle size distribution, the rate at which particles are being released, and the time over which the release has been occurring. Only took a few assumptions about particle density and refractive index. combined with scattering models developed over decades of cometary studies, to estimate that the dust grains are similar in composition to those from solar system comets, a mix of silicates and organics, fluffy aggregates rather than compact spheres. The fluffiness matters. Fluffy particles have more surface area relative to their mass, and surface area determines how efficiently a particle scatters light and how strongly it is pushed by radiation pressure. A compact grain and a fluffy aggregate of the same mass scatter light differently and follow different trajectories in the coma. The dust from comets is known to be highly porous, with structures resembling fractals, grains within grains, voids within voids, loosely bound aggregates that can reach sizes of hundreds of microns while remaining light enough to be lifted by moderate gas flow. These aggregates form in the cold of the protoplanetary disk, where dust grains stick together through gentle collisions, building up larger structures without compacting. The sticking is mediated by van der Waals forces, weak attractions between molecules that are sufficient to bind grains at low velocities. In the disk, relative velocities are low, meters per second or less, and sticking is efficient. The result is a population of fluffy, fractal-like aggregates that are incorporated into growing planetesimals. When the planetesimal later sublimates, these aggregates are released largely intact, preserving the structure they had in the disk. The dust in the coma of 3Phi/Atlas, if it is similar to solar system cometary dust, suggests that the object's interior retains this primordial fluffiness, that it has not been significantly compacted or sintered by thermal processing. This is consistent with an object that formed in the cold outer regions of a protoplanetary disk and has remained cold for most of its existence. The surface may have been altered by cosmic rays, by impacts, by previous episodes of sublimation, but the interior, shielded by tens of meters of overlying material, remains pristine. Only took millions of years of cold storage in interstellar space to preserve structures that are fragile, that would not survive significant heating or mechanical stress, that offer a window into the conditions of planet formation in a system that is otherwise inaccessible. The coma structure itself is informative, a perfectly symmetric coma, expanding uniformly in all directions, would indicate that outgassing is distributed evenly across the nucleus, or at least averaged over the rotation period. But the coma of 3I/Atlas shows asymmetries, subtle, not dramatic, but present. One side of the coma is slightly brighter, slightly more extended. This could be a jet, a localized source of enhanced activity, or it could be an effect of the viewing geometry, the way the nucleus is oriented relative to Earth and the Sun, creating shadowing or preferential illumination of certain regions. Disentangling viewing geometry from intrinsic structure is one of the challenges of cometary observation. The nucleus rotates, presenting different faces to the observer and to the Sun. The coma, which takes hours to days to expand to observable scales, integrates over multiple rotations, smearing out some of the short-term variability. What is seen is a time average projection, not a snapshot. Models must account for rotation, for the distribution of active areas, for the way gas and dust flow from the nucleus into the coma, for the forces that shape the trajectories of particles once they are released. The dust's trajectory is governed by a balance of forces. Initially, the dust is accelerated by the gas flow, dragged along as vapour expands from the nucleus. The acceleration depends on the gas density, the particle size, and the drag coefficient. Small particles are accelerated more efficiently and reach higher velocities. Large particles are accelerated more slowly and may not achieve escape velocity from the nucleus, falling back to the surface. Once the particle is beyond the dense inner coma, gas drag becomes negligible, and the particle's trajectory is determined by radiation pressure and gravity. Only took the invention of celestial mechanics and the later addition of radiation pressure theory to predict how dust particles move in the gravitational and radiative fields of the Sun, creating tails that point away from the Sun regardless of the comet's direction of motion. Radiation pressure pushes dust away from the Sun, but the strength of the push depends on the particle size. For micron-sized particles, radiation pressure can be comparable to, or even exceed, solar gravity, producing large accelerations. For larger particles, radiation pressure is weaker, and the particles follow trajectories that are more strongly influenced by gravity, falling behind the nucleus in its orbit. The result is a size-dependent separation, with the smallest particles forming a long, straight tail that points directly away from the Sun, and larger particles forming a curved, fan-shaped structure that trails the nucleus. The tail of 3I/Atlas is faint, visible only in deep images taken with long exposure times. Its structure is not well resolved. What can be seen is a diffuse extension in the anti-sunward direction, several tens of thousands of kilometers long, gradually fading into the background. The tail is not as dramatic as those of some bright comets, but it is unmistakably present, a testament to the dust that has been released and is now drifting away under the influence of sunlight. The particles in the tail will continue to move outward, slowly dispersing, becoming too faint to detect as they spread across the inner solar system. Some will eventually be swept up by planets, adding a tiny amount of extrasolar material to planetary atmospheres and surfaces. Most will remain in interplanetary space, drifting on trajectories that may carry them far from their point of origin. The dust, like the nucleus, is on a one-way journey. It will not return. It disperses, dilutes, becomes part of the solar system's inventory of microscopic debris, indistinguishable after a time from the dust produced by native comets and asteroids. The coma's inner regions, close to the nucleus where gas density is still high, are sites of chemical transformation. Ultraviolet sunlight breaks apart molecules, dissociating water into hydroxyl radicals and hydrogen, carbon monoxide into carbon and oxygen, complex organics into simpler fragments. These daughter species are what is observed spectroscopically. The parent molecules, water, carbon monoxide, methane, ammonia, are often too difficult to detect directly because their spectral lines are weak or occur at wavelengths where the atmosphere is opaque. The daughter species, by contrast, fluoresce brightly in sunlight, producing emission lines that are easily detected. Only took a few decades of laboratory spectroscopy and quantum mechanics to identify which emission lines correspond to which molecules, allowing the parent composition to be inferred from the observed daughters. With all the attendant uncertainties, the ratio of dust to gas, how much solid material is released relative to the amount of vapor, is a diagnostic of the nucleus's composition and structure. A dust-rich coma indicates a surface dominated by refractory material, where sublimating ice must drag along a large mass of dust. A gas-rich coma indicates a cleaner ice surface, where volatiles sublimate freely without entraining much dust. For 3I/Atlas, the dust-to-gas ratio appears to be within the range seen in solar system comets, neither unusually dusty nor unusually pristine. This is another point of resemblance. Another indication that the processes shaping this object are not fundamentally different from those that have shaped the comets observed for centuries in Earth's sky. The mystery is not what is in the dust, but what the dust reveals about the interior structure of the nucleus. Porous, layered, heterogeneous. These are the adjectives that describe cometary nuclei, and they supply here as well. But the specifics, how porous, how layered, how heterogeneous, remain uncertain, accessible only through models that match observations but do not uniquely constrain the underlying reality. The silence is profound. Billions of objects drift through the space between stars, and most of them are never seen, never recorded, never known to have existed. They move through the galaxy on trajectories shaped by ancient ejections and subsequent encounters, carrying no signal, producing no light of their own, reflecting none because there is no nearby source to reflect. They are cold, dark, inert. They pass through stellar systems without interacting. Their gravitational influence too weak to perturb planets. Their presence too faint to register on any instrument. The Milky Way is full of such objects. Estimates vary, but models suggest there may be more interstellar objects by number than there are stars. Trillions upon trillions of them, ranging in size from dust grains to planet-sized bodies, spread across the galaxy's volume. The total mass is uncertain, but it is significant, perhaps comparable to the mass in the interstellar medium, perhaps more. This material represents the detritus of planet formation, the objects that did not make it into planets, that were scattered or ejected during the chaotic early history of planetary systems. Only took a few simulations of planetary system formation, run on computers over weeks of processing time, to realize that ejection is not rare but common, that for every planet that remains bound to a star, many smaller bodies are flung into interstellar space. The ejection mechanisms are well understood in broad terms. When giant planets form and migrate, they gravitationally scatter smaller bodies. Some are flung inward, toward the star, where they may collide with inner planets or be vaporized by stellar heat. Others are flung outward, gaining velocity as they swing past the planet in close encounters. If the encounter is energetic enough, the velocity exceeds the escape velocity of the star, and the object is ejected. The process is efficient. Simulations show that for every giant planet that ends up in a stable orbit, the system ejects tens of Earth masses of smaller material. Close stellar encounters also eject material. When two stars pass within a few thousand astronomical units of each other, the gravitational perturbation can strip objects from the outer regions of each star's planetary system. The Oort cloud, the distant reservoir of comets surrounding the Sun, is particularly vulnerable. A passing star can deflect Oort cloud comets onto orbits that send them into the inner solar system, or onto hyperbolic trajectories that eject them into interstellar space. The Sun has experienced many such encounters over its lifetime, and each one redistributes material, some lost, some captured, most unchanged. Collisions between planets or large planetesimals can also produce ejecta. If the collision is energetic enough, fragments can be accelerated to velocities exceeding escape velocity. The impact that formed Earth's moon is thought to have ejected material not only into Earth orbit, but also into interplanetary space, some of which may have achieved escape velocity and left the solar system. Similar impacts in other systems produce similar results. The galaxy contains fragments of shattered worlds, pieces of planets that no longer exist, dispersed across parsecs. Only took one large impact, or a few, in the history of each planetary system, to see the galaxy with fragments that carry information about processes too violent to observe directly. The interstellar medium between the stars is not empty, but it is sparse. The mean free path, or the average distance an object travels before colliding with another, is enormous, measured in light years or more. Collisions between interstellar objects are rare. An object like 3I/Atlas, travelling at tens of kilometres per second relative to nearby stars, might go millions of years without encountering another interstellar object of comparable size. Encounters with stars are more common but still infrequent, occurring perhaps once every few 100,000 years. Most of the time, the object travels through empty space, experiencing only the gentle tug of the galaxy's gravitational field and the sparse bombardment of cosmic rays and interstellar dust grains. The loneliness is not metaphorical. The object is isolated in a way that is difficult to convey. The nearest star is light years away. The nearest other interstellar object might be millions of kilometres distant, invisible, undetectable. There is no interaction, no exchange of energy or information, no connection. The object moves through the galaxy like a ghost, present but imperceptible, part of the inventory, but not part of any process that would make its presence known. The silence is broken only when an object passes close to a star, close enough that the star's light warms it, illuminates it, makes it visible. This is a rare event for any given object. The probability that an interstellar object will pass through the habitable zone of a star, the region close enough for liquid water to exist on a planetary surface, is low. The probability that it will pass close enough to be detected by telescopes is lower still. Most interstellar objects complete their journeys through the galaxy without ever being illuminated, without ever producing a coma, without ever being observed. Only took the invention of automated surveys and sensitive detectors, and a few decades of operation to begin detecting the tiny fraction of interstellar objects that happen to pass through the solar system during the brief window of human technological capability. The objects that are detected are biased toward those that are intrinsically bright or that pass unusually close. Faint objects at large distances remain invisible. Small objects, unless they outgas vigorously, are too faint to detect. The population that is known is not representative of the population that exists. This is a fundamental limitation of observational astronomy. The sample is skewed by the selection effects inherent in the detection process, and correcting for these biases requires modelling, assumptions, and statistical techniques that introduce their own uncertainties. The universe is full of ejecta, full of material that has been scattered, collided, ejected, and now drifts through the space between stars. Some of this material is primordial, unchanged since the epoch of planet formation. Some has been processed, heated, irradiated, collided with, altered by the environments through which it has passed. The diversity is likely enormous. Rocky fragments from terrestrial planet collisions, icy fragments from giant planet zones, organic rich material from the outer regions of disks, differentiated material from bodies that melted and separated into cores and mantles before being disrupted. All of this is out there, invisible, uncatalogued, drifting through the galaxy. 3I/Atlas is one example, one data point in a distribution that is vast and mostly unknown. It is not special except in the sense that it happened to pass close enough to be seen, and that it arrived at a time when humanity had developed the technology to detect it. The object does not care about this. It continues on its trajectory, indifferent to observation, governed by forces that do not depend on whether anyone is watching. The galaxy recycles material, but slowly. Objects ejected from one system may, over hundreds of millions of years, be captured by another, or they may collide with planets, delivering extrasolar material to planetary surfaces, or they may fall into stars, vaporized and incorporated into the stellar photosphere. But most objects simply continue to drift. Their orbits around the galactic center, carrying them through different regions of the disk, past different stars, through different molecular clouds, without ever being captured or destroyed. Only took the mass of the galaxy and the timescale of its rotation to create a system in which material circulates, mixes, and redistributes, but on timescales so long that individual objects can traverse the disk multiple times without interacting significantly with anything. The silence of interstellar space is not peaceful. It is not restful. It is simply empty, the emptiness that comes from distance, from the absence of matter, from the vastness of space relative to the size of objects. The object drifts through this emptiness, a small, cold, dark speck in a galaxy full of such specks, none of them aware, none of them connected, all of them following trajectories determined by forces that operate over timescales far longer than the existence of any individual object. The galaxy does not notice, the universe does not record, the object moves, and the motion continues, unwitnessed except for this brief moment when a star's light makes it visible and a civilization with telescopes happens to be watching. Only took the coincidence of position and timing to interrupt the silence, to illuminate one object among countless others, to provide a fleeting glimpse of a population that is otherwise invisible. A reminder that the space between stars is not empty but full, populated by the remnants and rejects of planetary systems, each one carrying a story that will mostly go untold. The departure is inevitable. The object reaches perihelion, warms, outgasses, brightens briefly, and then begins the long climb out of the sun's gravitational well. The trajectory is hyperbolic, unbound, and the object's velocity increases as it moves away from the sun, accelerated by the sun's gravity pulling it forward along the inbound leg and then releasing it with greater speed on the outbound leg. This is the slingshot effect, though in this case the object does not gain much energy. Its velocity at infinity will be only slightly higher than it was on approach. Because perihelion occurred at a relatively large distance, and the gravitational acceleration was modest, the outgassing continues for a time as the object recedes, but gradually the activity diminishes. Farther from the sun, sunlight weakens, surface temperatures drop, sublimation slows. Water stops sublimating first. Once temperatures fall below roughly 200 Kelvin, carbon monoxide continues longer, but eventually even CO sublimation shuts off as the object cools to the point where only the most volatile species, if any remain, can escape. The coma fades, the tail dissipates, the object becomes once again a bare nucleus, dark and inert, reflecting only the faint sunlight that reaches it at increasing distances. Only took a few months of heating to drive off some fraction of the object's volatile inventory, and now the cooling proceeds, returning the object to the cold dormancy in which it has spent most of its existence. Observations become more difficult as the object fades. The brightness decreases with the square of the distance from the sun and the square of the distance from Earth. As the object moves outward and Earth continues in its own orbit, the separation grows rapidly. The object also moves into different parts of the sky, requiring different telescopes, different observing schedules. Some telescopes lose the object as it moves too far south or too far north for their latitude. Others continue to track it as long as they can, squeezing a few more photons from each exposure, measuring position and brightness even as the signal-to-noise ratio deteriorates. The final observations are precious. They constrain the object's outbound trajectory, allowing the orbit to be refined, the non-gravitational acceleration to be measured over a longer baseline. Each additional data point reduces the uncertainty, improves the prediction of where the object will be in the future. But eventually, the object becomes too faint, and the observations stop. The last image shows a faint smudge, barely distinguishable from background noise. The last astrometric measurement places the object at a specific position with a specific uncertainty. After that, silence. The object continues to move, but it is no longer observed. It recedes beyond the detection limits of current telescopes and becomes, once again, invisible. The trajectory, extrapolated forward, shows the object leaving the solar system at a velocity of several kilometers per second relative to the sun. The velocity vector points in a direction that depends on the perihelion geometry, the non-gravitational acceleration, and the gravitational interactions during the passage. The direction is not random but is determined by these factors, and once the object is far from the sun, the trajectory is essentially fixed. The object will travel in a straight line, deviating only slightly due to the galaxy's gravitational field, moving through interstellar space at a velocity that is typical for objects in the local standard of rest. Only took one passage through the inner solar system, one brief warming to send the object back into the cold with slightly less mass, slightly different surface properties, and a trajectory that is now pointing in a new direction, toward the different part of the galaxy. The destination, if it can be called that, is uncertain. The object's trajectory does not point directly toward any nearby star. It moves through a region of space where stars are sparsely distributed. Typical of the solar neighbourhood, the nearest star in the direction of travel is several light years away, and the object's velocity is such that it will take hundreds of thousands of years to reach that distance. Long before then, the object will have cooled to interstellar temperatures, 3 or 4 Kelvin, its surface equilibrated with the cosmic microwave background, its volatiles frozen solid and locked beneath whatever dust mantle remains after the activity near perihelion. The object will pass near other stars eventually, but near is relative. A passage within a light year is considered close in galactic terms, but it is vastly distant compared to the scale of planetary systems. The object will not interact with those stars in any meaningful way. Their gravity will deflect its trajectory slightly, a small perturbation that changes the object's velocity and direction by a tiny amount over millions of years. Many such perturbations accumulate, and the object's path through the galaxy becomes a complex curve, shaped by the collective gravitational influence of countless stars. The galaxy itself orbits, the Sun and the object, and all nearby stars orbit the galactic centre, completing one circuit every 200 to 250 million years. The orbital velocity is roughly 220 kilometres per second, much faster than the object's velocity relative to the Sun. In the frame of reference of the galaxy, the object is not travelling in a straight line, but in a gentle curve around the galactic centre. Much like the Sun, the object and the Sun are both part of the galaxy's disk, both bound to the galactic potential, both following orbits that will carry them around the centre many times over the next billions of years. Only took the combined mass of hundreds of billions of stars and the dark matter that surrounds them to create a gravitational well deep enough to keep even unbound interstellar objects like this one from escaping into intergalactic space. The object's future is long and uneventful. It will drift through the galaxy for eons, occasionally passing near stars, occasionally traversing molecular clouds, experiencing the slow erosion of cosmic ray bombardment and interstellar dust impacts. It will not sublimate significantly, because it will not encounter another heat source unless it is captured by a star or collides with something, both of which are improbable. It will remain cold, dark, and inert, carrying within it the chemical and physical record of its formation and the brief warming it experienced during its passage through the solar system. That brief warming is now encoded in the object's structure. The surface has been altered, dust has been lifted away, volatiles have sublimated, a new mantle may have formed. The interior, shielded by meters of overlying material, is less affected, but even there, heat has penetrated to some depth, raising temperatures slightly, perhaps mobilizing some of the more volatile ices, changing the distribution of materials within the nucleus. These changes are subtle, but they are permanent. The object is not the same as it was before perihelion. It has been processed, marked by its encounter with the Sun, and it will carry that mark for the remainder of its existence. The object will likely never be observed again. It is leaving the solar system and will not return. Its trajectory is hyperbolic, not elliptical. There are no future passages, no opportunities for follow-up observations decades or centuries hence. The data that have been collected, the images, the spectra, the astrometry, the light curves, are all that will ever exist. These data are archived, stored in databases, published in journals, made available to future researchers who may reanalyze them with better models or compare them to data from other interstellar objects discovered later. Only took a few months of observations to gather all the data that will ever be gathered on this object, and now the object recedes into obscurity, its story told as much as it will be told, its mysteries resolved to the extent that they will be resolved. The hyperbolic departure is not dramatic. The object does not accelerate suddenly or produce a final outburst. It simply moves away, following the trajectory determined by gravity and the small perturbations from outgassing. The velocity increases gradually as the Sun's gravity pulls the object forward, then decreases gradually relative to the Sun as the object climbs out of the gravitational well. Though the velocity at infinity, the speed the object will have once it is far from the Sun, remains positive, ensuring that the object will leave. The distance grows, 10 astronomical units, 20, 50. The object crosses the orbits of the outer planets, Jupiter, Saturn, Uranus, Neptune. Though it does not pass close to any of them, the planets are elsewhere in their orbits, and the object's trajectory is inclined, elevated above the ecliptic plane, so the paths do not intersect. Beyond Neptune lies the Kuiper belt, and beyond that the scattered disk, and beyond that the Oort cloud, extending tens of thousands of astronomical units from the Sun. The object will pass through these regions, though it will not interact with them. It is moving too fast, and the density of objects in the outer solar system is too low for collisions to be likely. Eventually, the object reaches a distance where the Sun's gravity is negligible, where the velocity relative to the Sun asymptotes to the velocity at infinity. At that point, the object is effectively back in interstellar space, and the Sun is just another star in the sky, faint and unremarkable. The object continues on its way, moving through the galaxy, its trajectory now pointing in a different direction than it was before. But otherwise unchanged. The encounter with the solar system is over. The object has passed through, briefly illuminated, briefly studied, and now it returns to the silence and darkness from which it came. Only took a few million years to arrive, a few months to pass through. And now the object embarks on another journey that will last millions of years more, toward no particular destination, for no particular purpose, simply moving because that is what it does, governed by laws of motion and gravity that operate the same everywhere, indifferent to the brief moment when it was seen and measured and wondered about. What humanity feared about 3I/Atlas was not what the object is, but what it represents, the limits of knowledge, the vastness of what is unknown, the unsettling realization that the universe is full of processes and objects that operate beyond observation, beyond measurement, beyond the reach of instruments and theories. The leaked photo that promised revelation showed nothing alarming, nothing threatening, only an object that is ordinary in most respects, familiar in its composition and behaviour, a comet from another star system that behaves much like comets from this one. The fear was not of the object itself, but of the gap between expectation and reality, the gap between what can be imagined and what can be known. The fear is misplaced, or perhaps it is not fear at all but wonder, the quiet unease that comes from confronting scale. The scale of time, millions of years of travel, billions of years since the object formed. The scale of distance, light years between stars, parsecs across the galaxy. Distances so large that they cease to have intuitive meaning and become instead numbers, abstractions, coordinates in a space that cannot be visualized. The scale of the population, trillions of interstellar objects drifting through the galaxy, most of them never seen, never known to exist, their presence inferred only through statistical models and indirect reasoning. Only took a few centuries of scientific progress to reach the point where humans can detect and study interstellar objects. And yet even with that progress, the vast majority of such objects remain invisible, inaccessible, forever beyond the reach of observation. The object does not threaten Earth. Its trajectory does not bring it close to any planet. Its mass is too small to perturb planetary orbits in any measurable way. Its outgassing produces no hazard. The dust and gas released are dispersed into interplanetary space, diluted to insignificance, eventually swept away by the solar wind or accreted onto other bodies. The object is not dangerous. It is simply there, passing through, a visitor that arrived unannounced and will depart unnoticed by most of the solar system's inhabitants, observed and catalogued only by a small number of astronomers who happen to be watching the right part of the sky at the right time. The leaked photo, if it exists, shows what all the other photos show, a faint smudge, a point of light surrounded by a diffuse coma, resolved only marginally even in the best images. There is no hidden structure, no anomaly that defies explanation, no feature that suggests anything other than a small icy body outgassing as it warms. The photo is unremarkable, and that unremarkability is itself informative. It confirms that the object is a comet, that it behaves like a comet, that the processes governing its activity are the same processes that govern solar system comets. What is feared, perhaps, is the ordinariness of the extraordinary. Interstellar objects were once hypothetical, speculative, the subject of papers that explored what such objects might be like if they existed and if they could be detected. Now they are real, observed, catalogued, and they are not fundamentally different from the objects that have always been present in the solar system. They are comets and asteroids, icy and rocky, active and inert, varied in their properties but familiar in their behaviour. The universe is not stranger than imagined, or rather, it is strange in ways that are comprehensible, that fit within the framework of physics and chemistry and planetary science. Only took 3 confirmed interstellar objects to shift the discourse from speculation about what might exist to analysis of what does exist. And the shift is both satisfying and anticlimactic. The object recedes, and with it recedes the opportunity to answer the questions that remain. The isotopic composition, the interior structure, the detailed chemistry of the volatiles, the origin star. All of these are uncertain, and most will remain uncertain. Future observations of other interstellar objects will provide more data, more comparisons, more constraints on models, but this specific object, 3I/Atlas, will not be studied further. It is leaving, and the data that exist are the only data that will exist. The fear that the object might fragment, might disintegrate, might reveal something unexpected in its interior, is not realized. The object survives perihelion intact. The light curve does not show signs of splitting. The coma remains consistent with a single nucleus. The object is cohesive enough to withstand the thermal and tidal stresses of its passage, strong enough to remain whole, at least for now. Whether it will survive for millions of years more, or whether it will eventually succumb to the cumulative effects of cosmic ray damage. Thermal cycling and collisions is unknown, but for now it endures. The human relationship to interstellar objects is one of curiosity mixed with humility. Curiosity because these objects carry information about other planetary systems, other formation environments, other chemical histories. Humility because the information is fragmentary, the observations are difficult, and the conclusions are uncertain. The object does not reveal its secrets easily. It must be coaxed, measured, modelled, interpreted, and even then much remains hidden. The interior is inaccessible. The past is reconstructed imperfectly. The future is extrapolated with large uncertainties. Only took a few decades of detecting and studying small solar system bodies to develop the techniques and models that can be applied to interstellar objects. But the application is always tentative, always provisional, always subject to revision as more data become available. The object story is both specific and universal. Specific in that it is this particular object, with this particular trajectory, this particular composition, this particular rotation state, observed at this particular time by this particular set of instruments. Universal in that it represents a class of objects, a population, a phenomenon that is common across the galaxy. Every star system likely produces interstellar objects. Every star system likely receives them. The exchange is slow, the timescales are long, but the process is ongoing. The galaxy is not a collection of isolated systems, but a connected whole, linked by the objects that move between stars, carrying material and information across parsecs. The fear was that the object would be alien, incomprehensible, a challenge to the frameworks of understanding. The reality is that the object is familiar, understandable, a confirmation that the processes observed in the solar system are not unique. The universe operates according to the same physical laws everywhere. Gravity, thermodynamics, chemistry, atomic physics. All of these apply the same way here as they do in the birth system of 3/Atlas. Wherever and whenever that was, the object is a test of those laws. And the laws hold, the predictions match the observations. Within the uncertainties, the models work. What is feared is not what is known, but what cannot be known. The galaxy contains more interstellar objects than can ever be catalogued. Most of them will never be observed. They drift through the dark, moving through regions of space that no telescope will ever survey, passing near stars that have no observers, crossing distances that light takes years to span and that objects take millions of years to traverse. The existence of these objects is certain, but their properties, their trajectories, their histories, all of these are lost, unrecorded, part of a universe that is larger and more complex than any observational program can encompass. Only took the humbling recognition of the limits of observation, the realization that the detectable universe is a small subset of the actual universe, to understand that most of what exists will never be known, and that the known objects are representatives, samples, hints of a population that is vast and mostly invisible. The object continues to move. The fear dissipates, not because the object has been fully understood, but because it has been observed, measured, fit into a framework, assigned a place in the catalogue of known things. It is no longer unknown. It is no longer purely speculative. It is real, documented, analysed, and in being so, it becomes less frightening and more fascinating. The gap between imagination and reality closes, and what remains is not fear but curiosity, the desire to observe more such objects, to refine the models, to answer the questions that this object has raised and that future objects will help to resolve. The leaked photo proves only what was suspected all along, that interstellar objects are not fundamentally different from solar system objects, that they are the products of the same processes operating in different environments, that they can be studied and understood using the same tools and techniques developed over centuries of astronomical observation. The fear was unnecessary. The object is Comet. It behaves like a comet. It outgasses, tumbles, recedes, and eventually fades from view, leaving behind a trail of data and a set of questions, some answered, some not, and the certainty that more such objects will be discovered, each one adding to the understanding of how planetary systems form, evolve, and distribute their material across the galaxy. Only took one object passing through, briefly visible, briefly accessible, to demonstrate that the universe is full of such objects, that they are ordinary and extraordinary at once, familiar in their behaviour and exotic in their origins, knowable in principle but elusive in practice, and that the study of them is a study of deep time, of processes that operate over scales so vast that human lifetimes are barely a flicker. A momentary attention paid to something that has been and will be moving through the cosmos for spans of time that dwarf civilizations and species and the existence of worlds.